Okay, thank you very much to the organizers. I'm excited to be here and learn more about these surveys. So I was asked, and I'm very happy to provide an overview theoretically of primordial features, which is one of the great targets. In fact, it's a place where large-scale structure is currently ahead of CMB, from what I understand. And that'll be covered much more in the practical sense by Ben's talk coming up next. So what I'm going to try to do is provide a theoretical overview of the motivations for these kinds of testable effects. Okay, and you can see on the slide, there's a few general references that I would point you to for more on this. Okay, so what are we doing in general? We're looking to probe the probability distribution, which in its full glory is, a huge functional of the scalar and ultimately tensor modes, which could arise by tracing out other degrees of freedom that could have been around. And obviously, a priori, this thing can take many forms, and it can do so quite consistently with known constraints and with the physics of inflation, if we bring that in, which we will in this talk. So what it produces really does depend on the kind of physics that goes into it. That is the field content and interactions. And what we'll do for the purpose of this session is to aim for minimal assumptions, sort of in contrast to an assumption of minimality. And I'll try to make it clear what I mean by that as we go. And this will enable us to test and discriminate quite broad classes of interesting dynamics. Okay, so what do we mean by features? For this talk, I'll take that to mean any contribution to the power spectrum and also non-Gaussianity, which need not be scale invariant or nearly scale invariant, nor need it be captured by low point correlation functions. Okay, so in fact, these observables, interesting as they are, and I think we heard a lot about them yesterday. I was tuning in from home where I had to teach. They still don't capture signatures of kind of generic early universe dynamics. There's a trade-off between symmetry, which is a very special possibility, and genericity. And so it's interesting to, in addition to exploring the highly symmetric assumption, to instead explore the case where we put in minimal assumptions and consider, for example, couplings that can be as big as they can be consistently with inflation and with the known observational constraints. So this is something that we'll do at various levels: effective field theory, quantum field theory modeling, and even a bit of string theory, with a good motivation that this whole subject is in fact UV sensitive. And I'll explain what that means and why I say it. Just so you know, when high energy theorists use the term UV or IR, we don't mean UV or IR. We actually mean high and low energy scales, just to be clear. Okay, so let's start with EFT. So there's this beautiful analysis of the perturbations from inflation that simply brings in the breaking of time translation symmetry, the existence of a background slowly varying Hubble, and general relativity, and then writes down the most general action that you can write down consistent with that. It is in one form, in one kind of gauge. And the upshot of that is that it doesn't speak to the question of features, because the coefficients in this action can be arbitrary functions of time, and that translates to being able to be arbitrary functions of momenta of scale. So this is an important theory, but it doesn't is uninformative on the question of features one way or the other. Of course, you can make a strong symmetry assumption and boil it down to a few, say, shapes of 3-point functions and so on, but that is an extra sort of human introduced assumption that the theory doesn't tell us to do. Again, sometimes in physics, symmetry is the right idea. Standard model particle physics is full of interesting symmetries. Sometimes it might not be the right idea. Supersymmetry has not been observed, for example, even though a massive theorist has basically assumed it was going to be there. So we really don't know a priori whether symmetry or not is the right idea. Okay, so if we take that point of view, the question becomes, okay, so then what do you do? Because an arbitrary function is not something that we can test. It's motivated more physically, not just by the arbitrariness of that function, but also by the fact that if we imagine inflation being driven by some scalar field, its interaction with other degrees of freedom, including very, very heavy ones compared to the Hubble scale, makes a leading order effect on the very existence of inflation and also on, therefore, on its signatures, even things like the tilt and R, as well as these features we're talking about here, are significantly affected by the full model of inflation you might have at the quantum field theory level, which could include, in addition to the inflaton, massive fields that kick it around, or even lighter fields that kick it around. And in some full accounting of the physics, all those things do affect the process. So, but again, just testing some function isn't something that's practical to do. So we can take, various attitudes toward, or organizing principles toward this question. We can stick with the EFT idea and maybe some symmetry, but reduce it to instead of a continuous shift symmetry, a discrete shift symmetry. We can kind of, on the other end of things, bring in complete, UV complete dynamics. We can bring in some notion of landscapes, either the kind of ordered ones we get out of string theory or random ones that we postulate, drawing from such a distribution. And we can carry out calculations, making predictions for what would be seen from any of these points of view. And so what I'm going to try to do is to kind of explain a few of these and spend some particular time on an interesting intersection of the first two, which has to do with the physics of axions, where if you take a bottom-up point of view or you take a string theory point of view, you're led to an interest in the same kind of dynamics, which is this thing about a discrete shift symmetry. But I'll try to put that in context of a much wider class of possibilities that people have talked about in the community. Okay, so this is a natural target for what these surveys. In fact, I think Ben in the next talk will explain how it is that LSS already improves over the CMB for these types of signatures. That we'll talk about, particularly ones that do have a sort of oscillatory description with some regularity to it, which is harder to mask behind ordinary physical evolution. It's kind of like the AO and being oscillatory, but from a different origin. So it's already exciting in that sense. So I guess in the sense of Mark's comment earlier, it's already opened up discovery space and kind of closed it as far as loss goes. These are constraints, but it'll get better and better. Okay. Now, there's lots of possibilities. Let me start from one that was done now decades ago. One of the gems of Starbinsky, who we miss in this field greatly. You open up any of his papers and there's just some beautiful physics in there. In this particular one, not one of his greatest works, but it's a very interesting one. You simply say, what if there's a sharp feature, a sharp change in the evolution of the inflaton field, for example, just a sharp feature in the potential for whatever reason. It might come from a phase transition, for example. And let's work out the consequences of that. So starting from just the Gaussian part of it, it's a calculation of the variance of the field. It's a time-dependent background, and the time dependence that leads to the production of the scalar modes in this model has a kind of delta function in it from the sharp feature, and you can compute the amplitude for particle production from that. And when you do that, you get an answer that has oscillatory features in it. The calculation is very simple. It's like a quantum mechanical scattering problem. And the upshot of it is that you get what are called linear features. From this, it's features of the form that are written at the bottom here, which are simply sinusoidal oscillations with respect to the mode number K. Okay, and here's a preview of what Ben might cover to do with both the existing and forecast constraints on such oscillations. Okay, now let's come back to the kind of bigger picture motivation. As I stressed earlier, interactions with other fields will generically affect the inflaton potential and the rest of its action. So if you think even about some field that has a very heavy mass, like this mass m in this little model, so the field heavy, phi heavy, wants to sit at some value phi naught. In fact, as this light times heavy squared coupling builds up, what actually happens in the model is that the heavy field adjusts its value a little bit to the extent that the quadratic potential actually flattens out entirely in this model. And this is just a very trivial mechanical example that shows such effects can be important in inflation. In fact, the proper sort of Wilsonian way to say this is that you write down an effective theory now at the level of quantum field theory modeling of inflation as a whole, and you take some model to which you add some operator that could be generated by quantum gravity, suppressed by the Planck mass scale here. And if you're ignorant of this contribution from quantum gravity, you're ignorant of epsilon and eta, or basically the tilt. You're ignorant of the tilt at order 1. So this has to be a percent level variable, and you're ignorant about it at order 1. So there is a good motivation for at least considering this problem also beyond quantum field theory in quantum gravity. And so we do that in string theory. We don't know the theory of quantum gravity. Of course, string theory has some things going for it, like an entropy count for black hole physics. And so let's explore what it might suggest on the feature front. And that will come from it's the genericity of axions in the theory. So just to belabor this a little bit, because I want to justify taking these things seriously. If we go back to when we were building up toward the standard model, so some of us are old enough to have been around before the W and Z bosons were actually discovered. And before that, there was a theory building up that just described the interactions of protons, neutrons, electrons, neutrinos. And as you build up in energy, you would naively think the coupling is going to get strong, but actually it's UV completed there by the W and Z, and it's weakly interacting at the electroweak scale. And that's, of course, the celebrated standard model of particle physics. In gravity, we have something that, in broad brush is similar. As you go up in energy, the effective coupling is the energy divided by the Planck mass scale, or times G Newton. And it looks like it's getting strong. It may be that whatever UV completes it brings in new particles, similarly to the way that the standard model brings in new particles to Fermi theory. That is indeed how it works in string theory. It brings in a huge, lots of new degrees of freedom. But it does so in a way that's amenable to a weakly coupled analysis. And so we can proceed to think about inflation and this feature question there. So let me explain this connection to axions before then going through some of the other examples in turn. Okay, so string theory is an elaborate completion of gravity. It has extra dimensions. These typically are reduced on some manifold that would be curved and typically negatively curved. And those manifolds are rigid. They have very little in the way of massless or light degrees of freedom. But axions are an exception to that. They come from topology. There's kind of glorified electromagnetic potential fields, which if you reduce those on some internal space with topology, you get something like the low energy theory of a superconductor in the low energy effective theory of string theory. There are these terms that are quite analogous to what might be a more familiar interaction, the Stuckelberg coupling. In any case, here what happens is you have axions that descend from higher dimensional form fields given just topology. So these are as, if not more generic in string theory than is gravity itself in 4 dimensions, large radius gravity itself, because it's a topological thing. So anyway, you have many of these axions. They couple to quantized magnetic flux in the theory in a way that generates a kind of potential landscape that has an underlying periodicity, but which has on each branch a kind of flattened potential for the inflaton. The way features are going to rise here is that if you take this theory, which boils down to quantized fluxes coupling to an axion field A, if you shift A by some period, absorb it in a shift of the flux quantum number, well, you get back to the same thing. That's this branch structure. That's the underlying periodicity. And while at the same time, you have a potential energy that naturally drives inflation. So this periodicity is going to be the origin of the oscillatory features that we will consider. And so that's kind of the string theory origin story of this kind of signature, this kind of oscillatory signature. Again, from the effective field theory point of view, you can be motivated by symmetry again, if you wish. A discrete shift symmetry would also lead in the direction of the inflaton field, would lead to the same kind of phenomenology. Although there are some complications that we treated in the literature to do with the fact that everything adjusts with massive fields around. Okay, so if you take all that for motivation, then in this case, what happens is the oscillatory features depend not just on the mode number k directly inside the sinusoidal feature, but instead depend on it logarithmically, and that has to do with the way that the periodicity in the field phi translates into a periodicity with respect to the log of the co-moving scale k through the usual freeze-out relation that k over a is h. Okay, so there's some logarithmic feature to look for. Examples include both such features in the potential itself, also periodic modulations of heavy field masses in the problem. And those those are both useful to illustrate some of the feature physics that can come out. Let's start with the first one. It's again a similar calculation to the one that I quoted of Starbinsky earlier in the case of a sharp feature. Here it's just that the scattering problem has in it this potential that is sinusoidal in the field. The constraints of this as a kind of percent of the underlying perturbations is about 1%. And again, it's something that's much easier to go for as a next step in testing inflation, particularly with large-scale structure, than say the kind of holy grail of the more symmetric signatures like FNL equilateral, which is indeed very interesting, but far from the only kind of physics we can test and not the easiest thing to try first. Indeed, in papers of Dan Green and Ben and company, the results are leading over the CFB results already, and he'll tell us about that. Now let me say a few words about the case where this oscillatory feature is coming not because of the inflaton potential energy oscillating with the field, but instead these heavy massive fields having their masses depend on the field in some such oscillatory way. One of the interesting results of that is that, well, it's always when you have a time-dependent Hamiltonian in quantum mechanics, then you tend to excite the system. And in this context, that means producing these massive fields. And they can be heavy, as heavy as the scale 60 Hubble that I think we heard about yesterday, the scale of the kinetic energy of the inflaton field, and still make a testable contribution to the power spectrum. But in this case, what's interesting is that not only is there such a contribution to the power spectrum, but in a reasonable range of parameters, the signal is actually higher for higher point correlators than the 2-point correlator. And this is a very clean calculation of a paraproduction event that basically Bremsstrahlungs off scalar perturbations. This is a component of the shape of the non-Gaussianities, which actually factorizes. It's very, very simple, and it can be computed easily at any n. Well, Kendrick Smith and others wrote down the optimal thing to do with that, resumming all n, and basically it's a position space feature that you can look for. And they did this in WMAP. Large scale structure seems like the place to do it, and I think Oliver had told me he was going to do it. I don't know if that's happening, and that would be great to see what happens. But this is an example illustrating both going beyond dead symmetric scale invariance or near scale invariance, and also going beyond low point correlators being the best thing to do. Okay, this made me question a lot of our understanding of what is the best place to look for signals in general. And I'll come back to that toward the end. But for now, I spent some time on these kind of regular signals, these linear or logarithmic oscillations in K. But there's a complementary point of view that has been explored very nicely in papers of Dan again and company, and Dick Bond in a different way, where instead you try to motivate a kind of probabilistic view of the complicated landscape of scalar fields that might have been around in the early universe, and think about, for example, repeated particle production events, but sort of like what we talked about earlier, but not assuming that they happen in a very regular symmetric pattern. They need not, but you can still calculate what happens if you, say, draw them randomly in some natural way. And there, even if you don't put in scale dependence by hand in the distribution, you find that a scale dependent signature builds up. And this is basically because particle production kind of amplifies. Actually, this is another contribution of Starobinski from years ago in some form, but basically here, it's amplifying during a window where the particle production is a dominant effect. And that gives you both, in the ensemble average sense, and also, of course, realization by realization, a signature that has features in it. So this is complementary to the point of view of focusing on, you can, of course, study both cases, but it's complementary to the case of the very regular pattern that I was talking about with axions, for example, instead just drawing something randomly. Now, there's been a lot of activity generally computing things about perturbations in inflation. In some kind of loose sense, one might divide it into the two sides of the board that I've posted here, where on the left, one kind of assumes symmetry and then computes the consequences of that. And that can include combining an underlying symmetry with the idea that there probably are massive fields involved in the UV completion. And even then you get some interesting signatures, oscillatory signatures, although with those highly symmetric models where you turned off couplings, direct couplings of the inflaton to these other fields and only kept kind of derivative ones, the signatures are naturally a bit smaller, or at least more contingent on the fields being light. But that's an interesting direction that has seen a lot of activity lately. On the other side of the board, you try to do this minimality of assumptions thing. And I said a few things about that earlier, but one thing that I think is very interesting to try and sort out in the theory community, and also to see how it might or might not impinge on observational signals going forward, is to move forward from this lesson that we had, that it's not always the low point correlators that are the best signal. In general, what do we do to compute the strength of the tails of this distribution? Is there a way to get some kind of organizing principle for that? So far, what people have done is compute this in various models and found, a model-dependent strength of this kind of effect of the tail compared to the Gaussian, and to what extent it is in the realm of being strong enough to potentially observe. And I just think this is a forward-looking direction. Yeah, we have some plans to try and sort it out a little more with Misha, who has worked on PDF analysis of large-scale structure, as well as these authors, Oliver and company, who have worked out how to deal with endpoint functions in large-scale structure. So I think there's a future for this in at least really sorting out what's the case. And these signals may or may not be scale invariant. Generically, things are not scale invariant. So that's why I include it in this feature discussion. Okay, so I think I am a little early, which is good. I want to give Ben plenty of time or have some questions that are not urgent, which would be great to have some discussion. But this feature searches really sit in a sweet spot where the observations from large scale structure are already ahead, where, they're as well motivated as anything in theory, I would say. I mean, people have their own views. I personally think we should do both cases of the dead symmetry or not, but there's no principle that tells us we must focus on one or the other. And these kinds of things are well worth testing, and they're kind of the next step as far as I understand things. The thing I should stress before concluding is that I have not provided, and I do not have any kind of threshold for them, which we have the luxury of having for R, for example, with the Planck field range, or even with, say, equilateral non-Gaussianity, even taking that symmetry assumption, where there's a level of it that would discriminate slow roll inflation from inflation where the field slows itself down by its own interactions. So it's not that in this business there's some threshold that I'm aware of that we can just say aim for that. But there are plenty of discoveries that have happened in, I think the discovery of the CC itself. The only threshold there may have been sort of anthropic, which is not what theorists were saying to do. And so, digging deep as far as we can go on these things, I think is perfectly well motivated, despite the absence of a threshold. But I do want to stress that we don't have that. I could imagine it coming out if we do understand the theory better. It is complex when we bring in all the relevant physics. But right now, I don't have a threshold to propose. Yeah, there's these sort of, again, break up into sort of regular features, regular structures, or random things. Obviously, the dynamics on the Earth is a very different thing, but you'd be surprised to go out onto the trails and find just a dead flat trail. So let me leave you with that.
Thank you very much. We have time for a couple of questions. Any questions from the audience? One very nice one. I guess in practice we do search for primordial homogeneity with well-known interpret and then we also search for primordial features. Doesn't make any sense from a circle point of view to some kind of joint searches, or how does that inform the search for homogeneity?
Yeah. I hope I didn't go too fast to be reasonably clear, because these oscillatory non-Gaussianities, their overlap with the symmetric ones is essentially zero. So you do have to do them separately. So maybe that's not your, well, they just have to, like, one doesn't imply anything interesting about the other. And again, there's no theoretical reason that we should stop at the 3-point function level also. But yeah, was that your question? Or yeah.
Maybe if I could follow up on what you just said. So the algorithm that we have can actually right now measure up to 6-point function, but there's no real reason we couldn't measure up to the 10-point function. It's just forming more combinations of the spherical harmonics. So are the inflation people in a position to give us a set of, here are like 10 endpoint functions you want us to measure, go do it? My sense has been that the only calculations I've seen have sort of gone up to the 4-point level, but not beyond, which is part of the reason we, didn't go too much beyond with the algorithm, but we could if people wanted that.
Yeah, I think, there's no like general calculation of the endpoint function in any possible model. What there is some examples where people have, it's a nice kind of semi-classical saddle point calculation to figure out the sort of strength of the tail in model by model. It's kind of related to large deviation theory. But the one case that I would point to where it was a relatively easy calculation to do a simple component to the shape. I should say there are other components that don't factorize like this. But anyway, is this one. And here the answer is known, and also the resummed answer is known. So yeah, there's definitely an example, which is not unreasonable. Of
this one, all the endpoint functions.
Yeah.
Sorry, this one has in principle all the endpoint functions.
Yeah, they have they take a very simple form. It's basically like a separate Bremsstrahlungs of radiation, scalar radiation off of these particle production events. So, and yeah, there's already an optimal estimator of it that people have done in the CMB, but given everything else that's been said about LSS already being ahead on this, seems like, this case could be analyzed there. But yes, but yeah, so that's just one example.
One last question for Eva. All right, let's thank Eva again. Thank you so much. Next speaker will be Ben Waterton on the same topic.
Speak on this mic. You can have this one.
That's fine. Eva, can you, Eva, can you stop screen sharing? Or is it not? Otherwise, I can't. Great. It's great to be here. Thanks for having me. I was tasked with following up on the great introduction by Eva on why primordial features are very interesting from a theoretical point of view and connecting that to the observations and to Spec S5 more specifically. And I want to start with this, I think, rather bold hypothesis that primordial features at this point are the best science driver we have for a future spectroscopic survey, such as Spec S5. And for the rest of the talk, I will now go through and tell you, given these points, I can go through these points to kind of underline why I think that's the case, culminating in like a conclusion at the end. In particular, I'll just briefly rehash some of the things that Eva was saying on why they are these imprints, these inflation imprints are well motivated theoretically. Then we'll go into details, as Eva was already mentioning, on why they're easy to extract from observations and what the current constraints are in comparison to the CMB, where Eva again kind of already mentioned the punchline, and then also mentioned like what the improvement is for the future and Spec S5. So starting with theoretical motivation, again, we've now heard this a few times, both yesterday and again today, that so far we see the primordial density fluctuations as being Gaussian and almost scale invariant, as given by the primordial power law power spectrum, with the reconstruction shown here by Planck. But as Eva kind of really laid out for various examples, there's definitely kind of a lot of room for primordial dynamics to exhibit a significant departure from scale invariance. So yesterday we talked about departures from Gaussianity. Now primordial features are departures from scale invariance. And so in a kind of relatively broad class of models, in particular when you go beyond the simplest single field slow roll monomial potential models, we do see kind of some of that kind of also related to additional energy scales in the problem and so on, especially when we then connected, as kind of Eva was highlighting, to fundamental physics and really kind of trying to write down complete models of inflation in the early universe. And so these departures from scale invariance then lead to kind of scale-dependent departures from the minimal kind of power law power spectrum that we kind of know and love. As is kind of shown here on the right-hand side, the almost scale invariant power spectrum is shown kind of in orange here, with potential kind of departures, and which we call features, kind of superimposed in the different colors. So overall, there are kind of two main kind of oscillator classes that Eva already mentioned as well, which are either the sharp features, which are those that arise from just a temporal kind of departure from the overall attractor evolution of inflation. Or we have these more these resident features, which are kind of ongoing, kind of all like over the evolution, over the time history of inflation, by just being a periodic oscillation around the overall attractor solution given by inflation. So that's what we're going to be kind of also mainly focusing on for the rest of my talk. But also let me mention that there are kind of correlated signals between not the power spectrum and higher point spectra. And so also with direct relations to primordial non-Gaussianity. So often features do have non-Gaussian signatures, whereas the converse is not necessarily true. In addition, what we're currently also trying to kind of look into with Dan, for instance, is that these oscillatory signals in the higher point spectra, as was also already alluded to by Oliver kind of yesterday, and I think we're going to be hearing about more from Sam kind of in the next talk, that we do see them also in the galaxy power spectrum through scale independent bias, and can hence kind of make progress in that way as well. Now, kind of one kind of downer to all this kind of great story so far is what Eva mentioned kind of at the end, that so far we don't really have kind of a clear kind of theoretical prior on the kind of the parameter space for these primordial features. I think in the future, with kind of more theoretical work, it might be possible to get something that might kind of go in a direction of the threshold we have for FNL local. So something that's a bit fuzzy and might only apply in certain circumstances. But at this point, I think it's just, we don't understand kind of phenomenal physics enough to really kind of directly make a connection and put out a threshold of saying, okay, if you see this, or if you don't see this, then we learn something qualitatively new. But kind of notwithstanding that, I think we still should kind of really kind of go for it from a theory side and constrain these models. And so what has been kind of proven very useful is to take a phenomenological approach in terms of parameterizing these features, these departures from the power law power spectrum in terms of either kind of linearly spaced or logarithmically spaced features like oscillations. And so for the rest of my talk, I will color code the linearly spaced ones in blue and the logarithmically spaced ones in red, as is kind of shown here on a kind of linear kind of k-scale on the right-hand side. Okay. So that is kind of the first point kind of ticked off. So primordial features are very well motivated theoretically. So now let's look at observations. As we kind of also heard from Austin yesterday, all these kind of inflationary or primordial signals are getting imprinted in the later universe, in particular in our observations of the CMB and large-scale structure. So, okay, that's the first step. They're imprinted, we can look for them. The same thing as is true for non-Gaussianity is also true for these features. Now, how do they look like in large-scale structure? At the top, I'm showing the meta power spectrum kind of in gray, superimposed with the signature from these oscillatory features. At the bottom row, it's the same in real space. And so what you can already see here is effectively what you're looking for is a second BEO peak. In terms of the linear features, that's very clear. It's just an additional kind of sinusoidal oscillation with a frequency that sets the scale of the peak. For logarithmic features, that's of course kind of more spread out. But especially if you have like the linear oscillations kind of in mind as kind of a prototype, that's kind of a good way of kind of getting intuition of what's going on. Now, what has been the theoretical insight that has become very crucial in making progress here is that instead of looking at the overall matter or kind of galaxy power spectrum as is shown here at the top, where we have to contend with all kinds of problems. We just look at, similar to kind of BO analysis, we just look at oscillations. So we just divide out the broadband power spectrum and look at what I'm calling the BO spectrum, just the wiggle or oscillatory part in the power spectrum. And so there we now see, so again in gray, it's just the BEOs with kind of in color and overlaid the features at the 5% level. So that's at the moment already clearly rolled out, but just for illustrative purposes. And so what we did by doing this, we really kind of separated out the power law power spectrum, which is part of the broadband, which we're kind of essentially kind of throwing away. And now we're just kind of we're focusing on the oscillatory part in the power spectrum. We're also focusing on these oscillatory features by themselves. And so this really kind of allows us to kind of make progress and kind of really kind of make these measurements, because I will still have to contend with kind of nonlinearities and all that kind of related business in large-scale structure. What's really kind of crucial, and it's crucial to take that into account, but importantly, we can do that analytically. So we know how these nonlinearities look like. We can really kind of model them, which means we're not limited to the standard kind of K nonlinear scale of 0.2 or whatever kind of numbers we're floating given an EFT or something like that. But we can really use all the modes that are signal dominated and hence really use the full statistical power of large structural surveys. So that is the second point ticked off. Great, we can extract them from observations. Next point, what about kind of current constraints? Eva was already flashing these results where we kind of in 2018 derived or inferred the first limits on primordial features from large structure data. In this case, kind of BOS DR12, which has kind of which subsequently has also been done in the correlation function and then extended to eBOS. But so what we see is we have about order 1% constraints relative to the primordial amplitude. Now, what's striking is that comparing that to Planck, so in this case it's Planck 2015, but Planck 2018 is essentially the same. We see that over this range of parameters that we have access to with the BOS data, we're already beating the CMB. And I think that's a very powerful message. And so that just has to do with the fact that we can really kind of disentangle these oscillations from the broadband and can use the full statistical power of the survey. So that is the third point ticked off. Okay, the leading constraints at the moment are already coming from large structure and not the CMB. And now kind of going to the future, these are forecasts for kind of at the top, it's kind of BOS, that's the current kind of state of the art. DESI as well as Euclid will be kind of similar. We'll be able to improve by a kind of factor of kind of 3 or 4. And then kind of Spec S5 would be able to do another factor of 4 or 5. And so I think talking about kind of these kinds of improvements today, and not improvements in terms of like 20%, 30%, but factors of kind of 4 or 5 or more is very striking. And then in particular, if you talk about kind of a cosmic variance or sample variance limited survey in kind of the more distant future up to redshift of 6 or higher, then we could even go another kind of half an order of magnitude. And now kind of to top it off though, if you compare that to the CMB in these dashed lines, with the bottom one being cosmic variance limited CMB experiment, so like the best the CMB can ever offer, we see that over a sizable fraction of parameter space, DESI is projected to already beat what the CMB can ever do. I think that's a very striking endorsement of large-scale structure for large-scale structure probes of features, and why this kind of should be kind of top of mind for all large-scale structure surveys. And so to kind of look towards like what is driving these constraints and how we can kind of optimize the survey to get the most out of the features. It's really about kind of a large number of signal-dominated modes in as large a volume as possible, because the number of modes is just giving you kind of overall sensitivity in terms of the amplitude. But then also, if you increase the survey volume, we can push towards larger feature frequencies, given that it's that cutoff effectively is just given by the Nyquist frequency of your survey volume that you're observing. And so with that, that's also the fourth point ticked off. So there's huge potential for improvements. And so we should go ahead and do this. So kind of to summarize, I think the potential detection of these inflationary imprints could have profound implications for our understanding of fundamental physics. And even upper limits can really help in terms of like model building and kind of narrowing down this kind of vast theoretical landscape that Eva started to chart. As I was laying out in the last part of my talk, it's really kind of large-scale structure surveys are the way to go in order to kind of constrain these imprints and to connect to something that I think Ben was saying yesterday during the panel discussion. In this case, for features, we really are ready for prime time. If we had the data tomorrow, we could go ahead and do an analysis, more or less some additional checks that we have to do in order to check some approximations that we did in our BOSS analysis. But that is kind of very straightforward to do and could be done in a few months. So with that, I'm concluding and putting this up again, but one in Flash, kind of something that I kind of put in kind of small print up there. I had like the currently sitting there kind of at the same times. I'm kind of putting that larger and kind of want to kind of suggest that we kind of should really try and kind of go beyond just these features and let us try and maybe use that as an example of kind of finding other science targets that can be kind of on par or maybe even better than these. And so with that, I thank you for your attention.
All right, time for a couple of short questions for Ben.
Thank you for a very nice talk. For the BAO spectrum, could you just mention a bit like how you treat the nonlinear corrections? Is that also a concern when we compare to data?
I mean, so you're asking like what these nonlinear corrections are for BAO damping,
right?
I mean, so that's just the same as in the BEO. So if you have like the BEO peak, the large scale bulk flows in the universe kind of damp that peak, which translates into or spread out that peak, and which translates into an overall damping of the BEO oscillations in Fourier space. Now the same thing is literally going on with these features. I mean, in the linear case, you see it's an additional peak. And so large scale bulk flows will similarly kind of spread out that peak. But given the techniques kind of developed with the EFT of large scale structure or kind of time slice perturbation theory, we can really kind of IR with some kind of all these terms that are relevant for this and can just analytically compute the damping term as being like this exponential given by a damping scale that we can predict given a model.
I see. So I guess this still work only for the baryon photon. Like if I have looking at the dark acoustic oscillation case, I still wouldn't be able to use a same trick or
no, I think the technology should kind of work the same as in the BEO case.
Oh, so you think like the similar approximation can already be applied to the DO case? Okay.
Thank you. One last question.
I'll try
I think you can.
to save us a little time. And this was very nice. Could you go back to the slide you were just on where you showed the 2-point function? So here, it seems like for the left-hand type of feature, it would make sense to do the search in position space because it's really localized. For the log oscillations, it looks like they give you wiggles in both Fourier space and real space that would be washed out by the way we normally bin the 2-point function in real space because we bin it, so you're going to average them out. Do you have a thought about maybe a new observable that's like mixed between Fourier and real space that would be appropriate for these guys that oscillate in both spaces?
Well, I mean, I guess we generally can bin or can calculate kind of band powers or given also like the window function. So we all, and so that effectively sets like the cutoff in the feature frequency that we have access to, as I was mentioning the Nyquist frequency. Now, I mean, I guess one can in principle imagine kind of doing kind of a joint thing, but in the end, with these oscillations, we really kind of looking for something oscillatory on top of some like a broadband, and kind of extracting that's the important bit. Given that we can marginalize away the broadband and not care about it. So that's in that sense, that there might be maybe something gained, but I think like either way, in that similar to the BEO, kind of either one works as well.
All right. Thank you so much for this inspiring talk. All right, our next speaker will be Sam Goldstein, who will tell us about the cosmological collider.
Okay, great. So I'm Sam Goldstein. I'm a grad student at Columbia, and today I'll be talking about non-perturbative techniques for constraining the cosmological collider. This work is done with all my excellent collaborators listed here. It's based off of some previous papers we've written, but it's mostly work that's in preparation that will hopefully come out in the next few months. So the motivation is that, as we've already know, stage 5 spectroscopic surveys are going to help unveil the physics of inflation, and in particular, constrain primordial non-Gaussianity, potentially beyond the standard types we're used to. A nice template that we're interested in analyzing is the so-called cosmological collider scenario, in which you have particles of mass of order the Hubble scale present during inflation, which imprint this unique squeezed bispectrum on the primordial curvature perturbations. Roughly speaking, there are around 3 interesting regimes of this scenario. In the massless case, you have this scaling amplitude delta is equal to 0, and you get exactly what you expect from local non-Gaussianity. For an intermediate mass regime with masses of order the Hubble scale, you end up having this additional momentum dependence in the squeezed bispectrum. And then finally, you can have even more massive particles, in which case delta becomes complex and you get oscillations in the bispectrum. And so the goal of this talk is to focus on this intermediate mass regime to try and develop this bridge so that we can eventually start looking into constraining these oscillatory features in large-scale structure. So then the question is, how can we constrain this using large-scale structure? There's already been some nice work looking at this from the scale-dependent bias, but here we're going to approach it a different way, where we're going to say that you have this massive particle exchange in the early universe that imprints an interesting squeezed bispectrum on the primordial fluctuations. And the whole challenge is to try and extract this from the nonlinear correlation functions, which then have their own non-Gaussianity that's induced by gravitational evolution. And the nice thing we can do is exploit key properties of soft limits of correlation functions, whereby a soft limit, I'm referring to momentum, where one of the external momenta, or when we see the trispectrum and internal momenta, are much less than the other two, or all the other momenta. So in this case, I'm looking at this so-called squeezed bispectrum, where Q is much less than K. And the nice things about these are they have some nice theoretical properties. For example, they're protected by symmetries. In this talk, we're going to exploit this Newtonian large-scale structure consistency condition, which tells us that the ratio of the squeezed bispectrum divided by the matter power spectrum should have no 1/Q to some power poles. And importantly, these can be violated by primordial non-Gaussianity, but since they're symmetry statements, they apply at a non-perturbative level. So we can use them in regimes where traditionally we can't model the correlators using perturbation theory. And secondly, what's equally important is that you can tend to do non-perturbative calculations in these regimes using the separate universe approach, which I'll describe more detail in future slides. And I want to emphasize that methods 1 and 2 here have already been used to derive estimators for FNL local in a paper that my collaborators and I wrote, as well as some nice work that's done by Utkarsh, who will present this in the next session of inflation. But what we want to do is say, can we generalize these methods to the cosmological collider, in particular the bispectrum I showed in the first slide? And so the first thing we have to do is to validate a non-perturbative model, we need simulations. And as far as I'm aware, at the moment, there aren't many simulations with these types of models. So we ran our own suite of simulations using the same set of parameters as the standard Quixote PNG simulations, but with different primordial bispectra. And so I'm showing the linear bispectrum divided by the power spectrum in the top left panel. And so this orange one is the case you get for local non-Gaussianity with FNL local of 100. But we're interested in these intermediate regimes that have additional scalings where this delta parameter determines that, as well as different amplitudes. And I want to emphasize this ratio, as you can see, has these clear poles on the large scales, which is a violation of the large scale structure consistency condition. So we run these simulations and you get the redshift 0 matter fields. And by eye, you can't really tell the difference from the primordial non-Gaussianity. But of course, what we want to do is compute correlators and look for the signatures of the primordial non-Gaussianity in these. So in this talk, we'll focus on 3 different correlation functions. We'll look at the large scale halo power spectrum, which is imprinted by the scale dependent halo bias. We'll also look at the squeezed matter bispectrum and the collapsed trispectrum. But in principle, you can look at other summary statistics for these types of models. And I'm happy to share the simulations with anyone here if they want to try and constrain them with their own types of pipelines. And so here I'm going to go over the measurements that we have from these simulations. And the left panel, I'm plotting the scale dependent halo bias measured from our simulations. The middle is the ratio of the squeezed bispectrum to the matter power spectrum. And the right is the ratio of the collapsed trispectrum to the matter power spectrum. And it's a little hard to see on the left because the halos have shot noise, but it's very clear on the bispectrum and trispectrum that these simulations with primordial non-Gaussianity have very clear pole-like features on large scales. And so the goal of this whole work is to then take these simulations, derive a theory model for all these functions, and then fit these to the data to obtain constraints on this amplitude FNL that we set in the initial conditions of our simulations. And so now what I want to go through is how do we do the theory modeling for these simulations, in particular for the bispectrum and trispectrum, because if you look at the scales I was using to analyze these, they're in the highly nonlinear regime. I'm looking at redshift 0 matter field up to k of 1, and later I'll go up to k of 2. So how can you possibly model this? So traditional perturbative approaches are not going to work here, but the nice thing, as I tried to emphasize earlier, is that we can do non-perturbative techniques. In particular, when you notice the squeezed bispectrum is described by the modulation of a small-scale local power spectrum due to a long wavelength gravitational potential. And so this means that these contributions from primordial non-Gaussianity are sort of sourced by these potential derivatives of the nonlinear matter power spectrum to a long wavelength potential, which is very similar to the stuff we saw in Marilena's talk yesterday. And additionally, the contributions from gravitational non-Gaussianity are actually easier to model in this regime using the so-called response functions approach. So the following equation I'm writing here is a pretty generic model for the squeezed matter bispectrum that applies to a wide range of models in non-Gaussianity. The only question then is, how do you estimate this nonlinear potential derivative? And the way to do this is via the separate universe approach. And so the idea behind the separate universe approach is to ask, how do the small scale fluctuations respond to an overall long wavelength potential fluctuation? So here I'll go through a pictorial representation of this, where you can consider 2 small scale matter fluctuations with the fixed amplitude, but different momenta. And so in the case of Gaussian initial conditions, these are completely uncorrelated with the long wavelength fluctuations. So as you see in the top right panel, the 2 fluctuations do not respond at all to the long wavelength potential fluctuation. However, once you have primordial non-Gaussianity, this introduces mode coupling in the initial conditions. And for the bispectrum I showed on the first slide, you can show that this mode coupling is described by the equation shown here. Now, the interesting thing to consider is 1, for local non-Gaussianity, delta is equal to 0. And you see that the mode coupling is completely independent of k. And what this tells you is that the nonlinear modes respond uniformly to a change in the long wavelength potential. And this is exactly equivalent to changes in sigma 8, which is why for these types of models, you typically run simulations at different values of sigma 8. And this is how you analyze the response functions. On the other hand, the interesting thing about the models we're considering here is that when delta is non-zero, you get a scale-dependent response. So your small scale clustering now depends on the actual momenta, and the response is modulated in a way that depends on the value of k. And so what you can end up doing is actually computing the separate universe derivatives by running simulations where you modify the initial power spectrum according to the prescription shown on the bottom here. And you can show that the potential derivatives can then be evaluated by finite differencing these simulations. And so this gives us the last ingredient we need for our bispectrum model, because in the previous slide, sort of everything we had, we could easily calculate. We just needed the potential derivatives. And so then we plug that in and we fit for FNL from the bispectrum, and we get something that looks like this. You'll notice the first point is slightly off because these triangle configurations aren't squeezed enough. What I'm plotting is our constraint on FNL delta for the different simulations we've run all the way up to k-min of 2. So as you go all the way to k-min of 2, you're looking at very nonlinear squeezed bispectrum configurations. We find that on the top panels for all simulations without primordial non-Gaussianity, we get unbiased constraints. But more importantly, for the simulations where we've actually injected this primordial bispectrum, we also get unbiased constraints on the amplitude. And I want to stress that this is a non-trivial check for two reasons. One, we're going deep into the nonlinear regime where traditional approaches don't apply. But two, if I showed you the actual plots of the response functions, they vary by several orders of magnitude over the momenta range I'm considering here. So if we got the potential derivatives wrong, our constraints on FNL would be extremely biased. And of course, to take things more to an observational perspective, we can also look at the scale-dependent halo bias, because that's arguably the best way to constrain these models. And so what we can do is take the halo catalogs from our simulations, and we see that these types of models introduce their own scale-dependent bias that looks very similar to the local type model, although it has a suppressed scaling, and it also has this non-Gaussian bias parameter. And so typically this non-Gaussian bias parameter is totally degenerate with your constraint on FNL, so you need some prediction for it in order to ever infer FNL from the scale-dependent bias. And so what I'm showing on the right are we fix FNL and we fix delta, and we fit for the non-Gaussian bias parameter for different halo samples to study the B1, B5 relation. And it's pretty interesting because in the top panel, you see the normal predictions for local. However, for these types of simulations, you get an additional dependence of your bias parameter on the Lagrangian radius. And we see that our separate universe simulations that I used to fit the bispectrum, we can also use those to predict these non-Gaussian bias parameters, as well as we find that it agrees well with these universality assumptions. But I want to emphasize that this is all for halos, and for the context of galaxies, this will be much more challenging. And finally, in this last minute, I want to say, just because we've done it, is that we've also looked at the trispectrum from these simulations. And you can ask, what can we learn from the trispectrum? The first thing is we can go to higher order non-Gaussianity. For example, here I'm showing constraints on tau and L from our simulations. And this is an exciting way to probe beyond the usual non-Gaussianity people are considering. But also we can find a sample variance cancellation. Unfortunately, we find that if we do a joint analysis of the power spectrum plus bispectrum, we gain very little from the trispectrum. But if one considers an example where you don't know the power spectrum, we find that adding in the trispectrum gives us a pretty good sample variance cancellation to where we almost are able to recover the constraints that we had with the known power spectrum. So to conclude, particles with massive order to Hubble scale during inflation produce very interesting imprints on large scale structure that I think we should try and search for in future surveys. And there's been some work looking at these simulations a while back, but now is the time to start generating more simulations with these types of bispectra and really understanding how we can search for these features. In our case, we're focusing on non-perturbative models, but I also think these applications to the scale-dependent bias and calculating the non-Gaussian bias parameters is very important here. And I think there's a lot of fun stuff that we can do on these types of models that I've listed on the bottom. The ones that I think are the most interesting are, of course, going to oscillatory bispectra, and then also focusing on multi-tracer and how to calibrate these bias parameters. And finally, I think the most interesting question is, can we ever actually constrain the value of delta? We know the amplitude, we aren't sure if there's a theoretically well-motivated reason to constrain this, but if you're constraining delta, you're actually constraining the mass of these fields, but it's very hard to distinguish with a finite number of modes between these different values of delta. So thank you.
So when you consider the bispectrum and the trispectrum together, I think that most generically there's a covariance between those two measurements.
Yes.
Is that something you take into account, or is that like in the simulation, take into account the simulations?
Yeah, all covariances here are computed from I think in this case, I used 100 simulations, and we're using pretty small data vectors. But yes, if you don't take this into account, you'll find the trispectrum helps a lot. But
I mean, it helps a lot more than you would have thought.
yes, but yeah, they're
No,
highly
sorry.
correlated.
It doesn't help as much as you would think. Okay.
Oh yeah, if you don't take into account, you're going to think the trispectrum is more useful than it is.
Hi, thank you for the great talk. I was just looking up your paper earlier, even before your talk, so that's great. I was wondering, so you talked about everything measuring on the, like you said, for halos on the matter bispectrum. It seems like a really great way to get into the nonlinear scale. What would change actually if we're moving toward galaxies? Do you see major roadblocks, or like what would be the few things we need to take care of in order to actually, apply this kind of method to data?
Yeah, so I think the challenge with halos is mostly you then have these exact same issues you normally have with B5, but you have additional bias parameters that enter in the bispectrum, at least if you're trying to do this with the bispectrum. But you also have to, I think, be somewhat careful with modeling. We'd have shot noise. So here I'm going to K of 2 in these simulations. But if I took the halo catalogs to that regime, I'd probably find very little information because of the shot noise. And I think, yeah, there's additional effects. I think RSD could be challenging if we're looking at these very squeezed bispectrum configurations, but to be honest, I don't quite know.
Say a few words real quick about the RSD part. That seems super relevant.
Yeah, so on the one hand, I know very little about RSD and we haven't thought about it, but in theory, these symmetry arguments we're using, at least the existence of this pole is protected from RSD. But the question is then you probably would need to include these terms into your squeezed bispectrum model. And I'm not sure what the status is of doing like non-perturbative RST at these high values of K. So I don't have an answer.
Okay, cool. Thank you so much.
Thanks, Sam, again. So the next speaker will be Amar Makur, who will also discuss colliders.
All right, so my name is Amara. I am a grad student at UC Santa Barbara, and today I'm going to be talking about a work that I recently put out with my collaborators, Nathaniel Craig and Shivik Kumar, who is also at this meeting, again, about the cosmological collider. And so we had a nice introduction just now as to what the cosmological collider is, how we can use it, and the kinds of objects that we're going to be probing. So here's just a brief visualization of the physics that it's happening. So what we want to be able to do in the cosmological collider is take heavy particles during inflation. This could be either standard model particles that whose masses are lifted up, or some new particle that couples to the inflaton. And these 3-point curvature perturbations in the squeezed limit are going to display a characteristic oscillatory signature, which we can then connect to these observables of our 3-point correlators in the large scale structure, 21 centimeter line, and various other observables from the spectroscopic surveys. Okay, so here's just, again, a brief summary. So if our inflaton couples to these new heavy particles in the squeeze limit, we get this very interesting behavior in which we get an oscillatory signal that depends on the mass and spin spectra of the heavy particle in question if their mass is of order Hubble during inflation. And given that there's such a large range for Hubble, this has the possibility of probing physics that is at extremely high energies. And this is very exciting. So there's been a lot of recent interest on different models that we can look at with the cosmological collider, different techniques that we can use to make some of these computations, and as well as specific models and their signatures that would lead to observable primordial non-Gaussianities at the cosmological collider. So here's just a brief sketch of some recent headlines. And so the question that my collaborators and I wanted to ask is, let's say we have a cosmological collider, we have some spectroscopic analyses, and we want to be able to connect our underlying microphysics of a particular model with the observed FNL from these surveys. And so in order to do this, we need to be able to perform these calculations systematically and include all pertinent effects. And in order to do that, what we typically do in the case of a collider or most other computations is we look at the effective field theories of these models. And so in the case of the cosmological collider, if you are including an approximate shift symmetry, your inflaton is going to couple derivatively to these operators of some fields of heavy particles that you're looking to probe. And so these operators are then going to necessarily have mass dimension of at minimum 5, and a lot of times greater than 5. And so this is a challenge for EFTs, just because you have to consider operators of very high mass dimension. And as, of course, your mass dimension grows, the number of operators grow. And there are also several considerations that are kind of unique to the cosmological collider or any inflationary scenario. So instead of our usual EFT techniques of looking at S-matrix elements, we are interested instead at looking at this correlator at a fixed time slice. And so instead of having some known in-state, some known out-state, and some scattering that happens, we're instead just interested in looking at this particular correlator on a time slice boundary. And then, of course, these calculations are going to be taking place in inflationary backgrounds. So looking mostly in our study, we looked at de Sitter space. And mathematically, there are some special considerations that you need. So usually when you're writing down an EFT and you're trying to isolate the minimal operator basis, you need to get rid of your operator redundancies. And so your boundary terms, and so you need to perform things like integration by parts and field redefinitions in order to remove these redundancies. In de Sitter space and other curved spacetimes, it's not necessarily guaranteed that these boundary terms vanish. So this is something that my collaborators and I needed to check explicitly. And then also when you're doing these field redefinitions, they may shift the correlator itself. So there needs to be some special care put into constructing these EFTs in order to use them as a tool to compare our data with our model-dependent predictions. And so in our paper, we were looking at just a toy example of an abelian gauge-Higgs model in single-field slow roll inflation. And so not getting into too many details here, but if this gives you the following marginal Lagrangian, and at dimension 5, you can think about writing down the following operator, which has people in the literature have considered this before. And what you end up doing is if you take either the field definition or integration by parts approach and carefully check all of these boundary terms, you find that this operator is redundant in this basis. And so this gives us a starting point to define a minimal operator basis for a given theory. And when we do this, we uncover a large number of operators up to dimension 9. And so as with any EFT, this gives us a systematic organization of all of our operators, whether or not their contributing effects come in at loop level or tree level. And in our paper, we provide a prescription for how to treat these boundary terms more systematically in order to ensure that any basis that you are working with is minimal. And so this is able to then isolate all of the physical effects and all of the pertinent operators. And so for this specific example, we were able to find several new operators that had not previously been considered, specifically for these gauge boson interactions. Okay, so I just wanted to end with some future directions of this. So this is kind of a brief sketch of what we did in our paper. And we wanted to write this more as a blueprint for how to take a model and enumerate its effects in a cosmological collider scenario, or in general in any scenario in which you have a de Sitter space background. And so we looked at an abelian gauge-Higgs theory. These, of course, can be generalized to other methods, or these methods rather can be generalized to looking at other sectors, to be looking at non-abelian gauge theories as well, and then also different models of inflation. So, for example, you can also look at a curvaton scenario or a multi-field inflation scenario. The second thing that I wanted to highlight that I think there's a lot of opportunity for is in these precise computation of loop level effects. So in our study, we were able to uncover several tree level operators for our Higgs boson, but studying the gauge boson requires going mostly to loop order. And as you can imagine, these computations in de Sitter space at loop order are quite complicated. And so these methods are still being developed, especially on the EFT side, for how to do these computations. And I think this is a good opportunity for some EFT people to maybe get involved. And then in general, we can kind of think about extending our usual flat space EFT methods to considerations of these operators in inflationary spacetimes. Okay, so just a brief summary. When we want to eventually use the cosmological collider as a tool to probe underlying particles, to discover new particles. This is going to be quite a complicated endeavor. And of course, one important piece of this is that we need to establish a minimal operator basis in the same way that we did for the LHC with the Warsaw basis. And in these scenarios, our standard assumptions of EFTs require some special consideration. So these boundary terms that don't necessarily vanish need to be dealt with. And kind of the main point that I want you to take away from this talk is that there's just lots of opportunities for this collaboration, cross-collaboration with effective field theory and cosmologists. So especially when we're looking at writing down specific models and also looking at in a more model-independent way of constructing an EFT, a lot of these methods can be used in this similar kind of program the same way as you would for a traditional collider. Okay, thank you.
We have time for a couple of questions.
Hi, thank you for your talk. My question is, does the barrier to more complicated models, like moving beyond the abelian Higgs model here, is the barrier there more of a, I have a lot of operators in my EFT, or is it a matter of like handling all these different kinds of fields and their interactions on curved spacetime?
Yeah, so there's definitely kind of a bottleneck with the number of terms that you get with your EFT. So I think for us, we're able to write down an EFT for most models that we would want to look at, and we know how to do that really well. The thing that we are not as good at doing so far is looking at the specific non-Gaussianity FNL parameter that is generated for each heavy particle that you're looking at in the cosmological collider. So particularly for loop observables, this is very difficult. And there's a lot of development being done for methods to do these computations.
Thank you.
Last question for Amara. Right, let's thank Amara again for a great talk. Next speaker will be Henry. Coming, and we'll discuss hybrid full colliders.
Thanks. So 3 minutes. It's very glad to be here and just like learning a lot about LSS. And we have like say today, yesterday, later and earlier, we have a lot of talks about cosmological collider, primordial feature, etc. So right here, what we are trying to do is to do a relatively harmless approach to spice things up by adding isocurvature in this element, because most of the discussions up to now are like based on curvature perturbations. So it would be interesting for us, and I guess for some of you, that what happens in isocurvature and theoretically how to make these models like make sense. So I think that's what we are trying to do here. Let's see. Great. So isocurvature, of course, like right here, the primary goal, or like say the benchmark target, is the dark matter isocurvature. So dark matter makes up most of the stuff in the universe in terms of matter, of course. Here, so without specific mentioning, so in this talk, isocurvature means like a dark matter isocurvature, but you see there are many components, possible components right here. So it's worth thinking, oh, is that like any other ways to like tweak the other components? And currently, the CMB gives like very strong constraints on like isocurvature perturbation, but at large scales. So as we see in Peter's like talk yesterday, this is not necessarily true at smaller scales. So that's something that worth bearing in mind. And I'll just skip all the details and the theoretical motivations for cosmological collider, primordial feature stuff, just to bring back a very general statement. We are interested in like the physics principles or like symmetries or like the patterns of what's going on during the inflationary phase. And the cosmological collider is one of the way that we probe them, like say, cannot be reached by other experiment types. And specifically, I'm talking about FNLs, like intake this form factor like that reflects heavy degrees of freedom in the theory. And the classical feature, or you can imagine like cosmological collider as like a quantum state, like or quantum fluctuation, just like bumping with each other, or you introduce like a classical event, and then a classical feature is evoked as a collective mode of these heavy field. So how to introduce isocurvature? We just go back to our theme here. And as I mentioned, we are interested in like symmetries during inflations. And the simplest way is to introduce a very simple symmetry, which is a U1 symmetry, admit spontaneous symmetry breaking there. And the isocurvature is coming from the fluctuations of this goldstone mode. And as you like written right here, the benchmark is the axion, which like in particle physics buy you a lot of good. It's well motivated theoretically, or you can equally get motivated by string theory or other theories that axion-like particles is also a good target. And eventually through misalignment, this can get converted to isocurvature. So that's what we are going to do today. So we discussed several scenarios, like how to introduce these isocurvatures, not only just isocurvature collider, but also how to make them hybrid. So we start with the first scenario. So where we focus on the primordial feature by this like inflaton PQ field interaction right here. The steps are such that you inject a classical feature, like you break the scale invariance halfway the inflation, depending on your interest or your field of observation. But eventually, some heavy classical modes get excited. And right here, without being over redundant in theory, the classical heavy mode would be just the radial mode of the axion, or like the PQ field, which is a natural component of the theory. So you do not need to just add excessive complication in your theory. And eventually, these classical modes get kind of decayed, or like say, get involved in the 2-point power spectrum. And therefore, because the innate relation between the axion mode or like isocurvature mode and this radial mode, so you have larger feature relatively in isocurvature instead of curvature. So that's like say one way you can think about it. You can, in extreme cases, completely hide the curvature feature. So the leading observation effect would be in isocurvature only. We also discussed the hybrid 3-point correlator. So the classical features, if you expand the Lagrangian and do all the calculations, you can find these like patterns of injections shown in these like diagrams here. To me, the most interesting thing right here is it do reflect sort of like symmetry during the inflation. Because you have a remaining like a Z2 symmetry in this theory. So like say the axion or isocurvature mode must show in pairs. So the leading feature in like the leading hybrid mode you observe, hybrid mode somehow in some sense could boost your observation like sensitivity, but it shows up first in double isocurvature mode. Like say so you have curvature, isocurvature correlation, not like one isocurvature, not like all of them isocurvature. So I think that's something worth thinking, or like interesting. Then we move on to the second scenario where we just like go back to like say more like a traditional cosmological collider discussions. And in this case, the feature, or like say the physics pattern we're going to probe is the heavy fermions, because heavy fermions, as like show up briefly previously, for example in QCD axions, the heavy fermions kind of just basically natural part of the game, because you need to introduce the interactions with the standard model through this fermion loop. So heavy fermion is the component of theory, and therefore they will introduce non-trivial isocurvature bispectrum just directly right there. Of course, experimentally or observationally, this may be too small to observe. So we add a few components to, like, say, just spike things up by adding this inflaton PQ current interaction, which still respects the symmetry, but then you introduce the kinematic mixing between the inflaton and the axion. Therefore, it picks up a linear combination coupling. Sorry, the coupling with the fermion is with the linear combination of the axion and the inflaton instead. And consequently, we also introduce a large chemical potential because you like couple to the different helicities, left-handed and right-handed currents differently. Therefore, you introduce large chemical potential that can just enhance the particle production in one helicity instead of another. So which greatly enhances the observation potential. And because of this linear correlation, you also find you wake up all the hybrid correlators, and that they are just related with each other through like a simple algebraic relation. All right, so I'm running out of time, but I want to bring you some updates. Like, say, we are thinking about some of these interesting topics since like last time. Which in parallel, like a discussion with all these great collaborators. It's for us, like it's important to introduce or think about the possibility of other modes of isocurvatures. As for example, Mark just commented, like there could be like compensating isocurvature or isocurvature in baryon number, or like say neutrino maybe. So it's not limited to dark matter production. For example, we also interested in right here, we protect the symmetry, right, till the end. So UN symmetry is never broken, but in many cases, the UN symmetry, the better be broken for like some special need. And in that case, you eliminate all the massless mode in this isocurvature sector. And this is like both experimentally and theoretically interesting to think about, because like your spectra would be tilted, so observationally more games can be played. We are currently also trying to figure out like the CMB implication for this, because things are more or less to us under control there, while the LSS is a widely open question for us. But I expect some of the experts in the room have a better answer to this. Thank you.
Yeah, thank you for a nice talk. I just want to make sure I understand the way you separate the curvature and isocurvature mode. Is in this picture we're showing, is the isocurvature mode just correspond to the excitation in the angular mode?
Yes.
So it's kind of that give you a curvaton, and then you say that perturbation is the isocurvature.
Yeah.
And then the radial mode is the curvature perturbation.
The radial mode just because it's very heavy. So like say in our setup, it's like a heavier than 1.5 H, so it's disappeared. So you cannot observe it at larger scales. So the curvature is given by like say inflaton still. And then that's why we introduced this effective coupling between inflaton and the PQ field.
Okay, thank you.
Thanks for the nice talk. Maybe too naive. You're mostly talking about axion models, and all of your couplings come with some derivative terms. I'm wondering if any of your conclusion will qualitatively change if you simply consider some scalar field to the inflaton, like do you get isocurvature, do you still get all the features here? Oh, that's your next step?
In general, yes, but it's just like it's a benchmark while we started from axion, and therefore for many cases we need to respect the symmetry. But as mentioned right here, in many other cases, you'd better just like explicitly break the symmetry, and therefore you will just eliminate all the massless modes. And theoretically, we found it's interesting in terms of theory, okay, how to do the calculation and stuff, and this still remains open.
I see. So let me try to understand. You're saying in other models you have explicit symmetry breaking. You have massive modes, and what's the qualitative difference when you consider massive modes?
I think it's that you would have features or like okay, 3-point correlators with a natural tilt. That's the minimal thing you would expect.
I see.
Yeah, but how to do that and the quantitatively how it looks like, okay, remains to be posed.
I see. Thank you.
Thank you.
We now continue on axion with the last talk.
Oh,
Great. Hello everyone. You hear me? Thank you for having me here today. My name is Preesh. I'm a grad student at Harvard. And I'm going to be telling you about some recent work with my collaborator, John Stout, on understanding the phenomenology of axions a bit better in De Sitter. And along the way, also pointing out potentially a detection channel for axions. Okay, to get started, first of all, what do I mean by an axion? So I'll be using a fairly broad definition. So I'll call an axion just a scalar field which sees a compact field space, which is to say at each point in space, it takes values inside a circle. And the circumference of the circle is parameterized by the so-called decay constant f. So 2 pi f is the circumference of the field space. And the reason I'll take such a broad definition is because these axions can arise from various kinds of UV models. So for instance, string theory, which has a bunch of extra dimensions which are compactified, will lead to a bunch of axions with a wide range of decay constants. And the crucial part is that in these models, the decay constant really captures information about the extra dimension that have been compactified. So knowing F really informs you about the size of your extra dimensions. And these are really the kind of axions that I'll be focusing on throughout most of this talk. So not Peche-Quinn types of axions or QCD axions that Ling Feng was just talking about. So the main question is, can primordial observables help us constrain this F in some way? And the main observable that I'll be focusing on is the cosmological collider signal. Now, since we've heard so much about the signal already, I won't go into too much detail. The main point is that tree-level exchange of some heavy spectator degree of freedom during inflation will impart some characteristic oscillations into the primordial bispectrum. So there's this sign, nu log k long over k short that you see over here in the squeeze configuration, where the frequency of these oscillations is set by the mass of the particle being exchanged. But the other part of the signal is this decay that I've highlighted in red, this long momentum over short momentum raised to the 1/2, where this decay piece, this exponent of 1/2, is really just a consequence of geometry. It's set by the dilution of this field as it propagates through space by Hubble dilution. So now, if you introduce some decay channels for the sigma, this heavy field, then that's going to distort the long distance propagation of sigma. So for particle theorists in the room, you introduce a decay width onto the field sigma. And this decay width is captured by the so-called anomalous dimension. And it's going to affect the cosmological collider signal of sigma as well. It's going to change the decay piece from 1/2 to 1/2 plus this gamma. So this is what this is the observable that I'll be focusing on. Now, what I want to do is to take this heavy scalar and couple it to two cases, a compact scalar or an axion, or a light non-compact scalar, so something which doesn't have this circular field space constraint, and see if there's any qualitative differences between the two cases. So yeah, warning, I won't be too careful about factors of Hubble through these expressions, so don't worry if something seems amiss. So right, so first for the non-compact scalar, so it's just a regular scalar field with some mass, and I couple it to this heavy scalar using some quartic coupling. Now I can't make this field exactly massless. There's problems in doing that because, in a sense, the state that this field lives in broadens significantly, and so the exact massless limit, in fact, doesn't really exist for the scalar. So I'll work out expressions only in the at leading order as I send the mass to 0, and I can compute this anomalous dimension. It's given by a two-loop sunset diagram if you're interested. And there's two key features of this expression that I'd like to point out. One is that it's a square of something, so it's positive. So it's always going to cause a faster rate of decay in the cosmological collider signal of sigma. And the other crucial feature is that it depends inversely with the mass of the scalar phi. So it's extremely enhanced. And this is a consequence of what I was just talking about. The state that this field is living in is super broad. The breadth of this state is controlled by the mass of phi. So fluctuations of this field are super enhanced in this light limit. Right. So now let's contrast this with the compact scalar. So the compact scalar, in contrast, can admit an exact massless description in the free field. But the same issues plague the compact scalar as well, in the sense that its state is completely delocalized. And as a consequence of that, any interaction that you use to couple it to some other sector has to know about this gate symmetry that it sees, this 2 pi periodicity in field space. So we have to couple it to sigma using this cosine potential. And when we do that, we can compute its anomalous dimension. It's given by a one-loop bubble diagram. And now the answer depends, interestingly, on an important ratio. Now we have a useful dimensional ratio to play with, which is f over h. So this is the result for the anomalous dimension in these two limits of f over h. So I also keep track of f over h in terms of beta, which is like 1 over f over h. So in the limit where I decompactify this field, I send the field space radius to the field space circumference to infinity. It behaves as a non-compact scalar should. The anomalous dimension is positive, so it also causes a faster rate of decay in this limit. And the anomalous dimension is super enhanced. So it goes as 1 over beta, and beta is going to 0. But the interesting regime is where this beta is roughly order 1. Now there we see these oscillations in the anomalous dimension instead, which is damped by this exponential as a function of beta. And these oscillations are really a kind of resonance phenomenon where this compact scalar is really acting as a kind of reservoir of energy for this heavy scalar. And it's really enhancing the correlations of sigma at long distances. And this is a qualitatively different result from the non-compact scalar. So now it's possible for this anomalous dimension to be negative, which was not possible for a light scalar to do, for a non-compact light scalar to do. So this is my main point. So currently, as far as I know, there's no other way of generating a negative anomalous dimension in de Sitter. So tomorrow, if we were to go out and do an experiment, measure the cosmological collider bispectrum, measure specifically the decay piece of it, and find a negative gamma, it would point to the existence of a compact scalar in de Sitter. And just to reiterate, placing any sort of constraints on a detection of this compact scalar, or just placing any sorts of constraints on f, would in turn allow you to make some sort of statement about some compact extra dimensions that this that this axion may be inhabiting. And this is my main point. Well, I'll end early so that everyone can go to lunch, but thank you.
We have time for one or two questions for free.
Is there any way to distinguish the particular topology of the compact dimension or whatever the configuration space of the scalar is? Like, yeah.
That's an interesting question. I don't know. But it would be fun to think about, maybe.
For instance, Calabi-Yau threefolds, right?
I understand your question. But yeah, I don't know the answer. I haven't tried like putting a different, imposing a different field space topology. What I can say is that what really matters is like the fundamental group of your whatever field space you're living in. So in de Sitter, the way we actually carry out these calculations is on Euclidean de Sitter, which is a sphere. And you're asking the question like, how can I map, what are the different ways of mapping a sphere onto some field space? So, if you have some non-trivial topology, then you would pick up like, in effect, some like winding numbers, perhaps, if your field space topology is complicated enough. So that can have some real effects, and it would be interesting to think more about that. But thanks for your question.
What do you expect to happen in the 4-point function? What is it, just this expression, or is there more terms for the trispectrum of zeta that like, would it just be this expression with like another power spectrum in it, or do you expect the 4-point function to look totally different?
Oh, you mean like the 4-point function of the inflaton?
Yeah.
Yeah, in the squeeze configuration, effectively, you're just sending the sigma, the heavy particle on shell, right? And as long as you send the heavy particle on shell, then you're going to see the same anomalous dimension.
Yeah, so you would predict that there's an oscillating sign trispectrum as your.
I would predict that there's an oscillating sign trispectrum.
Yeah, you'd have a sign there. It wouldn't be like sine squared or something. It would be just straight sign.
Yeah, I believe so. Yeah.
Okay, thanks.
There's no more questions. Thanks, free and all the speakers. I believe we start again at 4.
How do I stop sharing? How do I stop sharing?
Red button on top.
I can't find my. Oh, okay.
You could send me your slide.
Oh yeah.
Anyone? Okay, well, it'll stay up here. Okay, so let's just get started. So happy to have Subik Kumar to start us with extending the range of the cosmological collider.
All right, so yeah, let's get started. So I'm very happy to be here. Really great to be back at Berkeley. I was tasked to talk about cosmological collider and its connection with the physics beyond the standard model. So that's what I'll be talking about. I'll be describing some mechanisms that can potentially extend the reach of the cosmological collider, and I'll explain what I mean by extending the reach in a moment. So there have been lots of activities in this field over the last 5 to 10 years. Very broadly speaking, you can categorize the activities in 2 ways. There have been like host of papers which have tried to use the fact that it's a very, very powerful probe of on-shell physics that can potentially operate at very, very high energies, especially if the Hubble scale during inflation is close to the current upper limit. You can access particles which are as massive as this or even more massive using these observations. And with that, you can test a variety of high-scale particle physics scenarios, such as grand unified theory, supersymmetry, along with other things. On the other hand, computing these correlation functions, you do require quantum field theoretic tools in de Sitter space-time or quasi-de Sitter space-time. And that has been the main reason why people have been thinking about novel ways of computing these correlation functions, especially using principles of symmetries, localities, and so on. We already had quite a few interesting talks in the last session on various aspects of the cosmological collider, ranging from more theoretical aspects to more observational aspects. And of course, all of this is very, very timely because the observations are almost here. We are going to probe a vast number of modes. So in this talk, I'll be focusing on how we can leverage these observations to potentially learn about very, very high energy particle physics that you won't otherwise be able to. All right, so we have seen these expressions for FNL before, but I just wanted to spend one slide on the central idea behind the cosmological collider. So typically, as the universe expands, there could be instants in time, or it could be more continuous. And during certain instants, particles can be produced. So here I'm showing such a particle production process. And this heavy particle which got produced, it can subsequently propagate on shell in time. So time is flowing vertically upward. And after propagating for a while on shell, this particle, they can, for example, decay into inflaton fluctuations, which I'm showing by these gray lines. Or it can also mix with inflaton fluctuations, as shown by this K3 line. Overall, processes like this, they would give rise to a non-trivial 3-point function. And if you compute their shape, especially in the squeeze limit, you find that there could be a very interesting oscillatory momentum dependence, especially for slightly heavier masses. The frequency of these oscillations, they're characterized by the mass of the heavy particle. And the angular dependence potentially can encode information about the spin of the massive particle. So the dream is, if we see a pattern like this on the sky, then by measuring these frequencies and angular dependences, one can potentially extract on-shell mass and spin information from those measurements. And that is very, very exciting because, as I said, the masses of this particle, they're close to the Hubble scale or even slightly bigger. And if the Hubble scale is large, you are accessing extremely heavy particles that you cannot produce in terrestrial colliders. So from a particle physics perspective, what are some of the thresholds? We, of course, have the electroweak scale here. We know the physics around here very, very well. The Hubble scale during inflation is unknown. It could be very high, close to 5 × 10⁻13 GeV or so. But then above that, we do have some interesting thresholds coming from a variety of BSM reasons. For example, if you think about the seesaw mechanisms for generation of neutrino masses, you could have right-handed neutrinos sitting around 10 to the 15 GeV. You could have states coming from grand unified theories, which can have masses of the order of 10 to the 16 GeV and so on. So these are some of the interesting targets to have in mind. But as you see, there's a bit of a gap. There is at least like 1 or 2 orders of magnitude between the current upper limit and these thresholds. And that is potentially problematic, because if you go back and if you ask what is really the size of the FNL or the size of the non-Gaussianity, you notice that for slightly heavier particles, there is typically some exponential suppression that I'm showing in red. And this exponential suppression is coming for a very simple physical reason. Quantum fluctuations, they have Hubble scale energies. So if your particle mass is much larger than Hubble, you simply do not have enough energy to produce this particle on shell. So you pay an exponential penalty. And that is potentially very bad, because if you plug in a mass which is even like 3 times Hubble, this exponential factor is 10 to the minus 4. So it's a huge suppression. And naively, that tells us that we are probably restricted to only a factor of few above the Hubble scale, and perhaps these interesting BSM states, they're out of reach, because the exponential suppression is going to be enormous in those cases. So I'm going to talk about a couple of mechanisms in which this exponential suppression would be absent. And in that sense, you can extend the reach of the cosmological collider in the sense that these very, very heavy particles, they can be produced in an unsuppressed fashion, and they can give rise to observable non-Gaussianity. So the key to this is to realize that there are more scales in the problem. And this is something we have already seen during the talks today, like earlier today from Ben and Eva, and also yesterday from the talk by Austin, where this aspect of symmetry breaking scale being a central scale was also discussed. So the point is, if you focus on a simple, slowly rolling inflation model, if you compute the power spectrum, you see that it's given by this quantity, where this scale phi dot is basically the rolling velocity of the inflaton field. And it at least has to be as big as 60 Hubble squared. So that is already a super Hubble scale that is present in these very simple descriptions. And then, as we heard today earlier, there can be other features on the inflaton potential. For example, there can be oscillatory features, there can be sharp features. And we really do not have a very strong prior regarding what the frequencies are associated with these features. And some of these features can operate at a scale that is much larger than Hubble. And in fact, these kind of features model are already very well constrained from the current data, as Ben was mentioning. So the question I'm going to ask is, can these extra scales, are they relevant in exciting these very, very heavy particles, which you would otherwise miss? So I'm going to start with a very, very simple example. Let's imagine you have some complex scalar field, something like the Higgs field. And you can ask, well, how does it couple to the inflaton? And a very simple way to do that is to write a dimension 5 operator, where you couple the inflaton phi to the current of the complex scalar field. But it turns out that if you just have this operator and the U1 global symmetry is completely preserved, then there is no effect, because you can do an integration by parts to remove this operator. But then if you have even a very tiny amount of soft breaking of the U1, as is shown here, then you already get interesting effects. For example, one metric you can do is that you can do some field redefinition to get rid of the first term here. And then you see that this kind of models, they predict some interactions between the inflaton and the heavy field, which potentially can have non-trivial time dependencies. So one way to see that is to write the inflaton in terms of its homogeneous value, phi 0, and the fluctuations. And then if you do some algebra, you immediately notice that this kind of couplings, they predict a rapidly oscillating quadratic mixing between the inflaton and the heavy field. And what that means is that you now have this extra scale, like the phi dot scale in the problem. And what that scale can do is that it can inject energy in the Feynman diagrams of interest. For example, the energy can be injected in a way such that you produce one inflaton quanta here and one heavy quanta, because there's a quadratic mixing. And subsequently, this heavy guide can propagate on shell, and it can decay into inflatons. And in the end, you land up with, again, a non-trivial 3-point function. But importantly, this scale little lambda, it's given by phi dot. It can be much larger than Hubble. And therefore, as long as the particle mass is smaller than lambda, while it can be much larger than Hubble, this particle can be produced without any sort of suppression. So that's kind of one simple message. In this paper, we computed the more, like putting in more precise numbers, the values of FNL. And you see like even a factor of 10 above Hubble, or even heavier particles, they can be produced, and the associated FNLs can be ranging from order 1 to order 10. And therefore, we can look for them using data. This kind of ideas also work for particles that have spin. For example, if you have fermions, you can play a same game of coupling the inflaton to the current of the fermion. And that can, again, lets you access very, very heavy masses, much beyond few times Hubble. Similarly, a similar type of coupling can also occur for a more axion-like coupling, where phi can couple to some spin 1 or some gauge bosons. And again, you can excite gauge bosons that you would not otherwise excite. So those are all good. So you can excite spinning particles, you can excite charged particles, but you can wonder what happens if you do not have either of them. So what happens if you just have a real scalar particle without any spin or any charge? In that case, this kind of coupling, the current coupling, does not exist because there is no charge. But this is where these feature models or feature mechanisms that we were hearing about earlier, they can be relevant. And one thing that can happen is that if you have these features, then typically when the inflaton moves around on the potential, along with some usual slow roll contribution, it can have a subdominant oscillatory contribution dictated by the feature frequency omega feature. And once again, if you have such a thing, then again, like very simple dimension 5 operators, they can again give you this rapidly oscillating in time type of quadratic mixing or cubic couplings that are dictated by these feature scales. And the physics then is exactly identical to what I was describing before. You have an extra scale in the problem, which is the omega feature. It can inject energy. It can produce this heavy particle, even if it's much larger than, even if its mass is much larger than Hubble. And in the end, you can again land up with a 3-point function, which can be observable. So once again, putting together various order 1 factors, you can see like you can have FNLs ranging from order 1 to order 10, even for pre-heavy particles. So these are just some basic mechanisms that can help excite pre-heavy particles. But moving beyond this, overall, in the context of the broad BSM scenarios, there have been lots of activities as well. Some of these cases, the particle masses, really, they need to be close to Hubble, given the current state of the art. So it is an interesting question regarding whether these mechanisms that I was just talking about, whether they can be applied in all these various contexts. For example, there are works on SUSY by Dan and collaborators, where scalars associated in supersymmetric sectors, they can have order Hubble masses, and they can give signatures. There are also signatures predicted from right-handed neutrinos associated with, for example, the seesaw mechanism. There are properties of the Higgs potential and the Higgs couplings, and also non-minimal coupling of the Higgs that you can explore using the cosmological collider, along with many other aspects. So overall, the particle physics folks, they have been thinking about how to use the cosmological collider to look for these otherwise inaccessible heavy particles. Yeah, I'm almost there. Yeah. So just to summarize, we already have like pretty much brand new constraints coming from Planck and BOSS data. That's work of Misha and Oliver with their collaborators. And that is already constraining particles with masses up to like few times Hubble, order 5 Hubble. One question is, are there sort of bottlenecks in going higher? from the theory perspective, there can definitely be mechanisms that can excite even a 10 Hubble or 20 Hubble particle. But of course, it remains to be seen whether we can actually extract all the signatures based on the current data. In some sense, because these particle masses are heavier, the frequencies you get, since that's proportional to the mass, these frequencies are higher. And therefore, if you want to capture that frequency, you do need good resolution. And you also need sort of a large hierarchy between the minimum K modes and the maximum K modes that you can access, just to see like the overall like full shape oscillations. Along with that, of course, some of these FNL values I was talking about, they were order 1 or order few. And as we have seen before, we do need improved theory modeling that models gravitational nonlinearities in order to isolate these new physics contributions from the gravitational ones. And as I said before, these mechanisms, they're pretty recent, and it remains to be seen whether these mechanisms are compatible with the variety of particle physics scenarios, either in the context of supersymmetry or guts, et cetera, whether they can be implemented and whether we can really access these very, very heavy particles. So yeah, with that, let me end here, and thanks for your attention.
Okay, any quick questions? We will also have a chance for discussion later, but yes.
Hey, Shavik, thanks for the nice talk. So you're thinking about heavier, can we go heavier? And if I ask you to think like ultimately big, what's the possible largest mass you can probe? Because you already showed the gut scale, right? 10 to the 16 GeV. It's probably orders of magnitude larger than Hubble, right? Can you really probe that scale?
Yeah, I think one partial answer to that is gonna come tonight. So we have posted a paper that's gonna come up. There is one qualitative difference, which is, it's kind of easy to explain physically. The kind of signatures I was talking about, these are signatures in non-Gaussianities, like 3 or 4 point correlation functions. But if you really have extremely heavy particles, you can have situations where they're produced very, very rarely. So they're not produced in large numbers, but they're produced rarely. But because they're so heavy, they sort of give signatures that are not optimally captured by the non-Gaussian corrections. So in those cases, you might want to look for example, direct position space searches like localized hotspots and so on the CMB, or like localized overdensities in the context of large scale structure. And based on the current result that we have put out, and it's gonna come up, Oliver, me, and other people, we find like you can even go to masses that are even 500 times larger than Hubble. So that's one way of like seeing what's the ultimate reach. Yeah.
Okay, that's pretty cool. Thanks.
Yep.
Okay, so the next speaker will be Jamie Sullivan on improved constraints on local non-Gaussianity from spectroscopic data with galaxy bias.
Okay, great. Thanks. Thanks. I am going to talk a little bit about some work that we did at the beginning of last year in this archive link here, doing some forecasts for something that might be a stage 5 spectroscopic survey. It was suggested that would be nice to hear about for this conference. So here I am. And since I only have 10 minutes, I'm very thankful for the fact that yesterday we got a really nice overview from both Oliver and Austin of why we care about PNG, in particular local PNG, and how local PNG shows up in cosmological correlators, namely through scale-dependent bias. And I'm also going to assume, given David and Kyle's talk at the beginning of yesterday, that we're all interested in making the best survey we can to constrain local FNL. It's just a question of how we're going to do it. And finally, one of the points on Olivier's worries slide yesterday during our nice PNG discussion was whether we were leveraging the B-phi dimension of multitracer. And so that is his quote up here. And because that I feel like is a perfect way to start this talk, I changed my title to use that quote instead. And the way I'm going to structure this is give a flavor of the results from this work before starting to turn the discussion back on you all as to how we might be able to construct a survey that uses multitracer samples with different B-phi to constrain local PNG. Okay. There's a lot of talk for the first slide. Oh, what happened? I guess I tried to look something up in the dictionary, so I can't advance the... Okay, there we go. This is the slide I'm not going to explain because it just should be already in your mind from yesterday, but just so that it can flash across your memory. The way that local primordial non-Gaussianity shows up in the power spectrum is through the scale-dependent bias on large scales. And if you want to be optimistic and constrain FNL with some knowledge of B-phi, you need to have some model for what B-phi is. The model for what B-phi has been historically is inspired by this universal mass function approach, where you assume that that halos or any tracer form based on the significance of peaks in the smooth density field. And if you do that, you end up with a form for B-phi as a function of B1 like this, where you have B-phi is proportional to the Lagrangian bias or B minus 1. It turns out that even for halos, this is not what B-phi actually is, and we certainly don't expect it to hold for galaxies. So this was realized from the very beginning. So we introduced this factor of P. And the factor of P can be fixed if you think you know what the deviation from the universality prediction is for your sample, or you can put some prior on P. But the factor of P matters. Okay. And if you don't know P, you will lose constraining power on FNL. So this is a plot I took from BOSS analysis done by Alex Barrera in 2022, where he showed that when you change P, it dramatically affects your constraints on local FNL through the standard power spectrum sort of analysis. And you may say, what's the big deal? What causes P to change? Well, several things can cause P to change. Just for halos, if you have a split by concentration, that's what each of these little 3 dumbbells are, splits into 3 different equal number density bins of concentration at fixed mass. You end up getting large changes in B-phi by factors of more than 10 sometimes. And this effect from color is actually even bigger. This is from a paper by Alex Barrera and Elizabeth Krause here. In orange, they're splitting a sample in half. This is from a hydro simulation. And you can see there's a large change in B-phi in orange here with concentration. It's the same as I was showing before for the halos, but now for galaxies. But if you split by G minus R color, that's this pink line here, there's an even larger change at the same linear bias. Okay, so if you get, there's reasons to think that we might get P wrong, and that could be a problem. And, okay. And one other thing you could think is that if we did somehow know how to model these changes in B-phi with properties of galaxies that are physical or observable, you might be able to do some multitracer analysis. And just to refresh you a little bit, multitracer analysis, the cartoon is that you have 2 tracers of the same underlying density field. So since they share noise, if you account for that, you can extract some large-scale signal like FNL, where you might think you might not have been able to do that. And the error on FNL local for the standard power spectrum analysis for 2 different samples scales like this, where there's a piece that depends on both B-phi and B1 of the first sample and B-phi and B1 of the second sample, which I've confusingly labeled here B sub 1 and B sub 2, but those are 2 separate samples and both have the linear bias. Okay. So if you can model what B-phi is, or equivalently what P is as a function of redshift for your sample, you can do a multitracer analysis, constrain FNL local. So if we make the assumption, like you saw in that color plot, that B1 doesn't change very much, and all of the change is coming from a change in P, basically a change in effectively assembly bias, you can say that this expression basically simplifies to something like 1 over delta p, where delta p is the difference in p between the two samples at the same linear bias. So you expect for single tracer as a function of delta p, you get something like this. And for multi-tracer, you get something like 1 over delta p. And we did a forecast for what we called mega mapper at the time, but the number density, given the numbers quoted yesterday, are not too off. And this is indeed what we see. It seems like you can go to arbitrarily large delta p and get a very small error on FNL in our forecast, which is idealized here for the power spectrum. And black here is showing you p equals 1 for single tracer. And blue here is showing you a multi-tracer where we split by delta p. And then these other lines I can talk about people who are interested in, but it's just to give a more fair comparison. Because in blue and in orange and green, I'm showing what happens when you just use one sample with delta p, with p changing by the same amount as delta p is changing in the multi-tracer case. Because when you change p, you end up getting a better constraint on FNL, even in the single tracer case. Okay, so yeah, this is basically what I wanted to show here. And just to get an idea of the kind of games you can play in terms of getting constraints on FNL, once you know how to model B-phi in the subsamples. This is a forecast that we did for SphereX, where there's the points, the legend on here is not that important, but it's just to show you that once you have these different number density samples for SphereX and you know something about how B-phi changes in them, if you assume that, you can get a large gain in the constraint on local FNL. And okay, I'm not sure how much time I have left, but okay, cool. So I will say a word about this, which is in a slightly more realistic case for simulated galaxies that are constructed to approximately reproduce the LRG and ELG samples from DESI. We assumed that we had some way to predict what B-phi was for those galaxies. And we also played these games where we split up each sample according to some assembly bias parameter that gave us B-phi, and you can get a large increase if you know actually what B-phi is for the galaxies you have in your sample. So now I think the main point that I want you to take away from this is that if there is some diversity in the B-phis of the samples that you're using in your survey, there potentially is some gain to be had. Now, the question is, how do you actually predict the B-phi and for each subsample? And that's one of the questions I have up here for you. Can we design samples with different B-phi? Like, can we predict B-phi? I showed this ridiculous thing where I ran delta P up to 100, but of course, that's not right. But where is the limit where we have some reasonable expectation of getting a sample with different delta Ps at reasonable number densities? And I think that's all I really have to say. Oh, except I wanted to connect to these, the exponent delta, like these low delta models behave somewhat similarly to FNL, and it might be interesting to connect these kind of very involved multi-tracer games to that kind of work as well. So thanks.
So can the next speaker set up, please? And meanwhile, questions.
Really nice talk, Jamie. One question for you. So so the model that Jillian presented earlier today, I think would be really potentially informative for being able to provide guidance on how to select samples according to with different values of P. Where there is sensitivity to P in terms of constraining power, there is also sensitivity to mischaracterization as a systematic. And I'm wondering whether it's also straightforward for you to be able to provide estimates on, for example, like we're not going to know P to floating point precision for any future survey, right? That's not in the cards. And so whether it's possible to do an estimate on not only how different does P need to be in order to get gains from multi-tracer, but also how accurately does P need to be characterized?
Yeah. So I mean, there's two things, which is the prior on P and then the systematic shift from what the actual P is. Yeah. And in one of the papers that I linked to from Alex Barrera and Elizabeth Cross, which maybe you saw, they showed that when they do multi-tracer and they introduce some systematic offset in their B-phi or equivalently their P, there's some robustness there. So we didn't look at that, but that there is some way that some traction can be had, maybe.
Thank you very much. I think we're ready for the next talk, which will be about constraining local primordial non-Gaussianity using long wavelength modulation of local small-scale statistics.
Hi, everyone. My name is Utkarsh, and I'm a postdoc at University of Wisconsin-Madison. And I'll be talking about a method for constraining local primordial non-Gaussianity, where we use long wavelength modulation of small-scale statistics, in particular the power spectrum. The work that I'm going to talk about is done in collaboration with Moritz. Okay, is done in collaboration with Moritz Munchmeyer, who is a faculty at the UW-Madison, and Kendrick Smith, who is at Perimeter Institute. And the work is based on these two papers, which have come out in the last 2 years. So I'll start by giving, in a very brief way, the essence of what we are doing. So we present two very related simulation-based approaches for tightening constants on FNL. The first approach is a non-perturbative approach, which is sensitive to FNL information in higher endpoint functions. I'll argue that it's a very neat formulation and use of what's called position-dependent power spectrum approach, which has been used in the past, has been formulated by several groups and used in the past. From a computational point of view, I'll argue that it's a very efficient approach in utilizing the higher endpoint functions, since we are able to capture FNL information in the squeeze by spectrum by writing it down in an efficient power spectrum, effective power spectrum way. From a modeling point of view as well, it's very nice because a lot of nuisance parameters that crop up in a classical analysis are captured easily in our formulation, in this formulation. And we will show that we can use this approach to go to very nonlinear scales, which have not been explored before. And in particular, we show that certain recent results where higher endpoint functions were used to constrain FNL, and where they found that information kind of saturates at quasi-linear scales, we'll show that our approach outperforms that. The second part is just an extension of this classical picture, the non-perturbative picture, where we replace a classical power spectrum estimator with a machine learning approach, and we find that it does a much better job in constraining FNL. And the basic reason why our formalism works depends on these two aspects. We harness the fact that in the presence of a local primordial non-Gaussianity, there's a large small mode coupling. And it is this feature, which is there in a PNG universe, is not there in a Gaussian initial universe. And this aspect is guaranteed by consistency relations. And by using these two effects, we derive a large-scale field called pi-f, composed out of a very nonlinear late-time density field. It could be matter field or halo field, which has this clean 1/k² dependence, very similar to halos. To give you the current status of primordial local non-Gaussianity studies and the motivation behind our work. So it is very well known and has been established over the last 2 days that scale-dependent bias of tracers at late times remains and will continue to remain one of the clean proofs of primordial non-Gaussianity. But we also know that it is not an optimal way of constraining FNL. There's much more information out there in a galaxy catalog. In particular, the very next higher endpoint function, which is the bispectrum, is sensitive to FNL. However, there are issues with extracting FNL information from the bispectrum. In particular, things become very difficult to model. There are approaches like standard perturbation theory or EFT, which can model the bispectrum very easily, very fast, but only up to a certain scale, quasi-linear or linear scale. And it's very hard to push beyond that. There are other approaches like simulation-based approaches. It could be a brute force simulation-based approach, or emulator-based, or HOD-based. But there are many issues with all these approaches, and And because of all these, proper utilization of FNL information in the bispectrum has so far remained a bit limited. But despite all these issues, people actually have used it, at least to linear, quasi-linear scales. And the state-of-the-art constraints that we have comes from AFT-based analysis by Cabas et al. And D'Amico et al. With full authors written below. And the best constraints are of order 20 to 30. But the problem, the question is still not resolved. We still don't know how much more information we can extract from higher endpoint functions. And we don't know what is the best way to do that. What is a manageable, computationally manageable way to do that. And in particular, several recent reports have suggested that there's, in fact, no information, not much information beyond quasi-linear scales. So after giving this intro, I'll just go into my our approach, where the main idea is, as I said before, and as was covered by Sam and Oliver, the main idea is that you can write down an auxiliary field, which we call pi f, in terms of small-scale local power spectrum of late-time fields on observable f, so which can be written something like that. So you're filtering out using a filter hard modes and squaring it to capture this local power everywhere in your 3D volume. This field could be meta field or halo number density, but for illustrative purposes, I'm gonna just assume it's meta. And turns out the behavior of this meta field on the very large scales can be very easily written down in terms of a constant bias model, similar to halos, plus an additional term in a non-Gaussian universe, which is captured by that 1/k² term. The cross spectra with matter is sensitive to squeeze bispectrum, while the auto power spectra is sensitive to the coalesced trispectrum. And all the nuisance that I was talking about earlier, nuisance effects coming from small scale structure is captured by the Gaussian bias and a short noise like term over there. And this we established by the relations that I wrote was established by running some n-body simulations or utilizing QT and QT-PNG simulations, where we generated pi fields using different filters. And in the plot over here, we show how this 1/k² signature on the largest scale shows up in the pi field. The red curve is what we get in the data. And these pi fields are composed from meta field. You can do the similar thing with halo field, and you'll find a similar result. We also find that the noise is wide as conjectured in the last slide. So our conjectures, our modeling, simple modeling works out on the largest scales. And then we go on and look at its constraining power. So we perform separate universe simulations to estimate this beta pi parameter that appears, that is degenerate with FNL. But apart from that, we marginalize our other model parameters. And when we do an analysis where meta field is combined with the pi field, which effectively combines meta power spectra, meta bispectra, and trispectra, we find that we get a 2.2 times better constraints compared to a meta plus halo-based analysis, which can be seen here. And interestingly, we also find that our constraints keep on improving as we go to more and more nonlinear scales. So here I'm showing a Kmax of 3, which is even beyond the Nyquist frequency of our simulations. And we find that error bars on FNL keeps improving as we add more and more nonlinear scales. So this was all about a meta-based analysis. We then do a halo-only analysis where we have a pi field composed out of halo and combined with the halo density. And for a short noise level of QRD simulation, which is pretty high and pretty modest, our non-perturbative analysis finds that we only get a 20% improvement, which is also consistent with what groups have found on BOS data. In fact, Oliver's work, Cabas et al. Found similar constraints. And after talking about this classical approach, I next move to my second part, where what we do is simply extend our idea and replace the local power spectrum estimator by neural network architecture. We train this neural network on suite of simulations, we route down a loss function, drive it to minima, and you can see that this is the kind of pi we get after evaluating, training and evaluating it on unseen simulations. And when we run the same set of analysis, we find that we get a factor of 5 improvement compared to a halo plus matter kind of analysis, which is pretty cool. And yeah, so just to conclude, we have presented a neat method for extracting information from soft limits of density fields. It could be any field. And in particular, we have shown that FNL information can be easily extracted from this approach. We find significant FNL sensitivity on very low linear scales. And we also find encouraging signs that a future survey with large area and low short rays can exploit these high N1 functions to constrain FNL better. So yeah.
Okay, while the next speaker is setting up, can we, is there any quick question?
So you say that these future surveys with large area and low shot noise can exploit higher endpoint functions, but if they're just measuring halos and galaxies, then doesn't your plot that just showed the constraint from scale-dependent bias compare with the constraint from the bispectrum and trispectrum, and the fact that they're almost the same error, show that you're not actually getting anything out of the higher order endpoint functions?
Sorry, can you repeat that again?
So you have the constraints from the halo field, and
Yep.
for those, it looks like all the information is in the scale-dependent bias.
Yeah.
So then doesn't that tell you that you're not going to get any information out of going to the nonlinear scales with,
I mean,
like, it's nice that it's in matter, but we can't observe it, right? So
I mean, we do get like 20% improvements.
Yes.
For this modest density. We have also looked at higher density sample and we have found a slightly better result.
Okay.
And yeah, these are exclusively coming from halo bispectra on smaller scales with squeezed triangles with 2 hard modes.
Okay. Thank you.
Yeah.
Thank you. So our next speaker is Xinyu Chen on probing primordial non-Gaussianity by reconstructing the initial conditions with machine learning.
Thanks, Eva. Okay, so my name is Xinyu Chen. I'm a graduate student at Yale. Today I'll talk about probing a new approach to probe primordial non-Gaussianity by reconstruction. So this work, sorry, let me minimize this. Being done together with my advisor, Nikhil Paramanabhan and Daniel Eisenstein. So, okay. Wait, what is? Sorry. Paused. Go ahead. Use your link. Open Zoom again. Yeah. Yeah. It pauses your screen share when you full screen it for some reason. Oh. I think you'll just have to do it not full screen. I don't know why it pauses when you. I think you'll want to just share it like that. So maybe try this. Try sharing this. Or if you do this, and then can you just. Is that for some reason, I don't know, when it pauses the screen share whenever you full screen it. So is that, I don't know. Okay. That's probably what I would try to. Okay, so we don't know why. So I'll present like this. All right, so right, so this talk will be focused on the local type FNL, but this reconstruction can be applied to constrain other types of primordial physics, and I'll also mention this in the end of the talk. Okay, so just a brief summary or a recap of local FNL constraints, current status of constraining local FNL with large-scale structure. We already heard a lot, so I'll try to be quick here. So the current status, the current best measurements with larger structure survey has sigma FNL about 20 using the EBOS quasar sample. And the state-of-art technique is this scale-dependent bias on galaxy power spectrum, and this scale-dependent features on very large scale. So so the systematic is very large, and it also suffers from cosmic variance, although this can be mitigated with multi-tracer analysis. And forecast for DESI with this method and single tracer analysis shows that the sigma FNL will be about 10. So we still need to improve on that. And so adding bispectrum can add more information so that can tighten our constraints. So for example, Spherix studies show that there'll be about a factor of 2 improvement going from power spectrum to a joint analysis of power spectrum and bispectrum. But of course, this factor depends on different survey configurations. But there's some benefits of using bispectrum, but there's also challenges. So gravity also generate very large bispectrum because gravitational nonlinear evolution generates non-Gaussianity. So that's a confusion when we try to measure the primordial non-Gaussianity. And then there's many triangles, so the data vector will be very large. So we can mitigate these 2 challenges. So for gravity-induced bispectrum, we can apply a reconstruction to remove gravitational nonlinearities. For large data vectors, we can compute near optimal 2-point bispectrum estimator to, and that's very computationally inexpensive. So this will be the focus of my talk. So I'll introduce a new approach to constrain primordial non-Gaussianity by reconstruction, and then apply reconstruction to this 2-point estimator. Okay, so first reconstruction. So reconstruction here means reconstructing the initial conditions. That's reversing a late time density field back to the initial density field. So we want to go from this nonlinear density field to the initial linear density field. This technique has been mostly used in BAO analysis in the last decade, and we have a standard reconstruction algorithm to do so. So here's the performance of the standard reconstruction. You can see that this is the reconstructed density field is still very nonlinear compared to this initial condition. So this is not enough for primordial non-Gaussianity, and so we can do a better job by combining machine learning with the traditional algorithm. It's based on perturbation theory. So how do we do that? We first run a traditional algorithm, and then we get a reconstructed density field, and then we train the neural network with reconstructed density fields. So this is the performance of this combined approach. So now here, this is much better than before. This is much closer to the initial condition. So the reason why this works well is because CNN is very local, so it doesn't have access to information outside the receptive field, but perturbation theory works very well on large scale, so it provides very good approximation on large scales. So we use traditional algorithm for large scales and then CNN to focus on smaller scales. So this is the performance in terms of cross-correlation coefficient with the initial condition. This is the pre-reconstruction nonlinear density field, and this is a performance of a traditional algorithm. Here is not a standard reconstruction, but the details don't matter here. And then this is the combined approach. So we can see that this hybrid method performs significantly better. Okay, yeah, so this is matter density field, and in real surveys, we need to consider short noise. And so I select a halo field samples to mimic the DESI year 1 LRG sample in terms of the effective number density, B square M bar. So here is the B square M bar about 1.7 times 10 to minus 3 per microparsec cube. That's very similar to the LRG sample. So here we can see that there's still some improvement, but it's not as significant as what we saw earlier in the high number density matter field. So there will be benefit if we have a higher number density sample. Okay, so let's go back to the matter density field. So now then I train a model with simulations without PNG and apply that to simulations with PNG. So here these three lines correspond to FNL plus 100, 0, minus 100. And we see that this still works very well. So a model trained with no PNG simulations work very well for simulations with PNG. So now we have a reconstructed density field, then we can go to constrain primordial non-Gaussianity. So instead of computing the bispectrum, we look at a different summary statistic, and that's also a bispectrum estimator. Okay, so we study this cross power estimator in the form of phi squared delta. Phi is the primordial potential, and delta is the linear density. So if you recall, the local FNL captures the phi g square field. So cross correlating, so to the first order phi square is the phi g square, and so cross correlating phi square with delta will reveal the FNL term. And so computationally, phi can be computed using the linear delta. So here, both these two deltas can be approximated by the reconstructed density. And then, so this is very easy to compute. It's like a two-point statistic. So, okay, so here this phi square is in the configuration space. So it's a convolution in Fourier space. And then when we cross-correlate that with the delta, then we'll have a bispectrum in the integrand. So this cross-power estimator is an integral of bispectrum, but it has access to higher K information because of a convolution. So this is also a near optimal bispectrum estimator, which is first proposed by Schmidt-Foll et al. Okay, so here is the cross-power estimator. So I am comparing reconstructed version with initial conditions for FNL plus 100, 0, minus 100, and I applied different smoothing schemes. Here's Gaussian smoothing at 10 megaparsec and 5 megaparsec. And here's a cosine filter, so between k equals 0.2 and 0.25, and then we have a hard cutoff at k equals to 0.25. And then these three lines are the corresponding pre-reconstruction for FNL plus 100, 0, minus 100. So you can see that the separation between different FNL values get very large after reconstruction. So signal to noise get very large. So reconstruction can remove most of the gravitational nonlinearities and strengthen the primordial signal. And we also see that there's some discrepancy between reconstruction and the initial condition. So CNN here represents the hybrid reconstruction. So there's some discrepancy. So there's a little bias for the estimate of FNL, but this bias can be calibrated with simulations. Okay, so yeah, here we also see that the cosine filter works the best. So in terms of the Fisher error, sigma FNL for the cross power in the 1 gigaparsec volume, because we are using 1 gigaparsec volume simulations. So the nonlinear density, we can get about sigma FNL equals to about 76. And then after reconstruction, you can get about 50 at K max equals to 0.1. And here are the results for the three smoothing schemes. And these are pretty close to initial condition. So after reconstruction, we can get about a factor of 1.5 improvement. But also reconstruction recovers the linear K modes up to higher K, so we can use a higher K max. So going from 0.1 to 0.2, we can gain another factor of 3 improvement. Okay, so here this forecast is for a single parameter, FNL. So that's a little optimistic without including other bias terms, the squared density and shift term and tidal term. All of these are degenerate with FNL, and especially the square term. So we need to include those terms, and so we can do that by computing similar cross-power estimators. Okay, so to summarize, this hybrid reconstruction can remove most of the gravitational nonlinearity and strengthen the primordial signal. The cross-power estimator is very easy to compute, and it's very powerful to estimate FNL. And the application of reconstruction on the cross-power estimator give us low sigma FNL although there's a slight bias, but we can calibrate this bias with simulations. So here's some of my ongoing work with Nikhil and Daniel. So we're including the quadratic gravitational bias terms in the model. We're developing probabilistic machine learning models to do a better reconstruction for high shot noise bias tracers, and we're also applying this reconstruction technique to the non-local type primordial non-Gaussianity. And the estimator will be different. It's not only just the phi square delta, but plus some other terms. So this reconstruction can be potentially more helpful there because for equilateral and orthogonal, we can't rely on the scale-dependent bias approach. And we are also constraining primordial features with STESI data with this hybrid reconstruction. Okay, so this is to address Simone's request. So implications for future surveys. So there's still a lot to be done. I am working on those things. For now, we can see that reconstruction can benefit from higher number density samples. And reconstruction allow us to use higher K modes. So large volume may not be as important. But if we want to combine this approach with the scale-dependent bias, then we will still need a large volume. So both large volume and the higher number density, that might be challenging. But that's where local type, if we want to study the non-local type and primordial features, and this approach can be very helpful, and then we would benefit from higher number densities. Thank you.
Okay, again, next speaker, could you set up while we have a question or two?
Hi, thank you so much for the nice talk, Xinyi. Really interested in this method. Would you mind clarify a little bit your exact setup with the CNN? Like what's your training data? You mentioned you're mixing in perturbation theory on large scales, but it's a little unclear to me how that
Yeah,
happened.
so I can give a short answer, but we can discuss more later. The CNN setup is basically 7 layers of convolutional layers, but the perturbation theory step comes in the pre-processing. So we use the products of traditional reconstruction algorithms as our training data. So we train on that and to predict the initial condition. So the traditional algorithm takes care of the large scale, and then the CNN can focus on the smaller scales.
I see. So your inputs and labels are for your CNN are basically the pre and post reconstruction from your reconstruction algorithm.
The input is post reconstruction, post traditional reconstruction. And then the target is initial condition. Output is another density. It's density in, density out.
Okay, I see. Is that the post reconstruction is the first step?
That's right.
Got it. And then you have access to your initial conditions.
Yeah.
Thank you.
Okay, I think we need to move on, but there will be time for the discussion for more questions.
So thank you for having me here. I'll be talking about some work done by me I'll be talking about some work done by me with my advisor and collaborators on theoretical systematics in large-scale galaxy surveys, which aim to measure local primordial non-Gaussianity. And sorry, I'm not able to. Local primordial non-Gaussianity presents us with a really useful scale-dependent bias signal that increases quadratically at the largest scales. And I won't talk too much about this because this has been gone into thoroughly in this conference, except that a signal like this, which increases at arbitrarily large scales, can only have a primordial origin because any post-inflationary effects eventually have to die out beyond the Hubble radius. But realistic surveys don't go all the way to the Hubble radius, and therefore non-primordial horizon scale effects can interfere with this signal and present as theoretical systematics. By the way, I should confirm that when I say theoretical systematics, I really mean modeling challenges, which can worsen our measurements. So yeah. So I'll start with a more familiar and probably less important effect, and it's the effect of free streaming light relics. Light relics are particles which are relativistic until pretty late times, and their free streaming affects the coupling between structure formation at small and large scales, with the effect that the galaxy bias at small k, that is at large scales, is suppressed as compared to galaxy bias at small scales. And when you try to infer FNL from a measurement of the scale-dependent bias, you need to take into account this signal. Otherwise, your inference of FNL can be wrong. The right plot shows that the marginal change to the galaxy power spectrum due to free streaming is very small, and the shape is not increasing out to arbitrarily large scales. But so that's why it doesn't. If you model this effect correctly, your constraint on FNL is not worsened. But for realistic neutrino masses, say around the normal hierarchy or the inverted hierarchy, you can incur a bias in FNL of something like 0.2. And this is a result that I obtained in the context of the SphereX or the All-Sky survey, which aims to measure FNL at FNL of 1 plus minus 0.5. So certainly this effect is important if you want to constrain FNL that tightly. And the other more important effect is the effect of ionizing radiation fluctuations. And there's a background of ionizing radiation that pervades the universe created during the epoch of reionization. Ionizing radiation affects the rate of cooling of gas in dark matter halos and therefore modulates the distribution of observed galaxies. And incorporating this effect is very challenging because it needs a correct modeling of the astrophysical effects involved in galaxy formation. But this has been done to an extent by Matt McQuinn and others, and we used the model developed by them, whereby you can imagine adding an additional term to the linear bias expansion, which introduces an additional parameter called the intensity bias. And delta J is are the fluctuations in ionizing radiation. The intensity bias, BJ, encodes the negative rate at which the cooling of gas in dark matter halos is affected by an ambient ionizing radiation fluctuation. The effect of this on the galaxy power spectrum is twofold. There is an effective change in the galaxy bias due to the clustering of matter with ionizing radiation. And there's a short noise term which owes its origin to the fact that ionizing radiation is created by discrete sources, namely quasars. And analysis done by Matt McQuinn and others suggests that a reasonable value for intensity bias is somewhere between 0 and 0.1. Although in principle, this is a very difficult quantity to model, and even like modeling BJ at different redshifts for different galaxy samples is a very non-trivial problem. And the short noise term really only becomes important for near infinite quasar lifetimes. But if you consider quasar lifetimes less than or equal to 100 million years, which is like a good upper limit for quasar lifetimes, then the effect of this short noise is negligible. And this is an effect, the effect of ionizing radiation generally is large at higher redshifts. So I have a plot here on the right, which shows the marginal change in the galaxy power spectrum due to the ionizing radiation fluctuations as compared to the signal we want to measure, which is the scale-dependent bias, which is given by the orange curve. The dashed line shows the effect that you get when you have infinite quasar lifetimes. But otherwise, really, the effect of suppression, the ineffective suppression of galaxy bias due to the clustering of ionizing radiation with matter is what really dominates for reasonable quasar lifetimes. Sorry. And now you can ask two questions. If you model the ionizing radiation correctly, does it affect the precision on your FNL measurement? Or if you do not model it correctly, if you just ignore it at all, how badly does it bias your measurement of FNL? So for the former question, our left plot shows constraints that we obtain on FNL, provided we incorporate a correct model for the ionizing radiation fluctuations, as well as, and we incorporate the astrophysical prior that BJ is somewhere between 0 and 0.1. And we really see no significant difference in the precision of the measurement of FNL. But on the other hand, if we do not account for this effect, if we ignore this effect, then you can obtain, sorry, there's a typo here. You can actually obtain, you'll get a negative bias in FNL because there's a suppression of the power spectrum. And this negative bias can be as large as like 0.8 sigma for the intensity bias, as large as 0.05. And this makes the effect more important than the effect of neutrinos. And certainly, it's also more challenging to model because the intensity bias is a very difficult parameter to model. And like the general theme in this conference has been go big, go deep, go deep. And the bigger you go, the deeper you go, the bigger this effect is. So consequently, it's going to be important for any future spectroscopic survey which aims to go to high redshift. So for instance, for megamapper, which goes beyond redshift equal to 2, this effect seems to exceed 1 sigma. So in that case, it's going to be more important. And yeah, as I said, theoretical systematic, by theoretical systematics, I mean modeling challenges. And I'd like to draw your attention to the well-known point that the scale-dependent bias signal is really just a measurement of the squeeze limits of all primordial correlation functions. So really, whatever you see using the scale-dependent bias should be understood as a combination of FNL, GNL, HNL, and so on. And in this case, the right question is to ask is how well can you constrain both these parameters with the galaxy power spectrum? And expectedly you can't do really well. The constraint on FNL obtained from the power spectrum for sphere X, which is about 1, becomes as bad as 2.5 for if you include GNL. Again, this okay. And as expected, FNL and GNL are very degenerate, so their covariance is like close to -1. This is consistent with what pretty much everybody has found. The challenge here is to model these Newton's parameters beta f and beta g, and beta f is basically the well-known parameter b phi, and we consider models which model beta f as b minus p, as was mentioned in an earlier talk. And yeah, and if you go beyond the simplest model with a primordial bispectrum and you consider primordial trispectrum, you should also really consider a collapse limit of the trispectrum, which leads to a stochasticity in galaxy clustering. And that can also be a way of measuring tau NL, which is a collapse limit of the 4-point function. And using the power spectrum, we also obtain constraints on FNL and tau NL. And again, for models with different values of p, the constraint on FNL is again degraded, but not as much as it is if you try to constrain both FNL and GNL, because FNL and tau NL are not as degenerate. The surprising thing or the noteworthy thing here is that while sigma FNL becomes more than 1, sigma tau NL kind of is less than 1, provided you consider values of tau NL which are large enough to give you a reasonable signal about the scale-dependent bias. And so what's worth considering is that sphere X might in principle be able to constrain tau NL more tightly at the expense of a degraded constraint on FNL. And the reason this fact is important because the simplest models you can write down for tau NL also have a non-trivial FNL. Tau NL is in general going to be bigger than like 6/5 FNL square. And if you unambiguously detect tau NL, then if you subscribe to these models, you have effectively ruled out FNL equal to 0. And that's kind of the whole idea of measuring FNL, at least at the 0th order, is to rule out FNL equal to 0, or to rule out if FNL is not equal to 0, and infer the existence of additional fields during inflation. So that's it. And yeah, I mean,
Great, thank you. Can the final speaker come forward? Right, and are there any questions here?
Okay, last talk of the session. So let's simmer things down and go back to 2-point correlation functions. So this work was done with my advisor, Daniel Chung, and Moritz Munchmeyer, collaborator Moritz Munchmeyer. So I'm going to assume here that all of us have to some extent, have some idea about what isocurvatures are, and so we'll follow it from there. Now, right. So what do we right now know about isocurvatures? I'm going to look at CDM isocurvature specifically. So we have here the dimensionless power spectrum and of course the scales in terms of the wave number k, the usual adiabatic power spectrum. And the constraints right now say that from Planck, the constraints are that flat or scale invariant isocurvatures are roughly about 1% or so, or maybe less than that. However, the same Planck paper, and in fact, there are several others in two and a few others, which actually found a 2 sigma hint, or they, rather than found, I think they suggested 2 sigma hint for something like a blue isocurvature. A blue isocurvature here refers to the situation where you have, where you, I think it's not C. Okay, I'll rather just, where you have a situation that n iso is greater than 1, so you have a steeply increasing isocurvature spectrum. And this is mainly a primordial power spectrum. So even if my isocurvature can have a power, let's say, of an amplitude as much as an adiabatic, the overall effect in the matter power spectrum is suppressed because you have transfer functions and you have additional suppression factors. Now, just to give a good idea of how do you get blue isocurvature from inflationary physics, you need something like a non-equilibrium dynamics. So let's assume that we have a complex scalar field. One can also assume this is a Pechequin field, U1 PQ. So I have some radial component here. I have some radial component and I have some axial component here. So you have a situation where initially the radial, when the U1 PQ is spontaneously broken, you have the situation where the radial field has a large wave. So it is displaced much away from the usual FPQ wave here. And so during inflation, this field starts rolling down. That's a non-equilibrium or the dynamical situation. And when that happens, while the radial field is rolling down, you get a blue tilted spectrum. So the modes, when they leave, they actually have their amplitudes frozen. So if a mode leaves initially, if a mode leaves somewhere here rather than a mode leaves somewhere here, you actually get a blue spectrum. But when the radial field settles to the minimum, you actually get a flat spectrum because now there is no more dynamics. Things are static. It's equilibrium stage. One can also look at the same situation in terms of the massless axions equation of motion, the fluctuation in the axial field. This is the massless case where the radial field is just sitting at FPQ, but now if the radial field is actually rolling down, you get this additional kind of a dynamical mass. And so which says that as long as the box R, or in this case, just the second derivative of R, as long as it is active, you have some mass, but when radial field settles, the mass disappears. So as long as axion remains massive, you get a blue spectrum, but as soon as radial field settles and the mass disappears, you get a flat spectrum. So essentially what it means that primordial blue tilted isocurvatures, and primordial here means that which is generated during inflation, in fact, have to have some kind of a cutoff. And in fact, if my n iso, the spectral index is greater than 2.5, and that 2.5 is largely, n iso is largely related with the mass of the spectator field in this case being the axion. So you have to have some cutoff. So there is a theorem behind this that you cannot detect in future an isocurvature with n iso greater than 2.5 and not have a cutoff. It has to have a cutoff. And that is something related to the dilution effects or the dilution of the energy density. And in fact, the same physics which dictates the slope or the spectral index of these isocurvature also dictates when it should have a cutoff. So naturally, one expects a cutoff to lie somewhere within 1 megaparsec inverse. Of course, I can always tweak my models and take this 1 megaparsec inverse to 100 megaparsec inverse or beyond. But naturally, one expects without much tweaking to lie within 1 megaparsec inverse. So this implies that if I have a situation where my isocurvature is not increasing indefinitely to very small scales, but rather cuts off like the orange one here, or maybe in this case, this also cuts off but has some oscillations. These are nicely well suited for large scale surveys because they will evade all of the constraints that we have been seeing from small scales. So then it becomes almost like a science task for large scale surveys to look for these kind of situations where you have blue isocurvatures, but those with a cutoff. Then we started looking at what sensitivity can future surveys have. We tried to answer this in context of Euclidean megamapper and use EFT of LSS. So from that perspective, EFT of LSS becomes a nice and good formalism. So you can do anything beyond lambda CDM, and in this case, it actually pays off. And we use bias tracer formalism, so lots of biases. I just want to mention that the Laplacian bias is something which is degenerate with certain spectral indices. So this is some kind of a degeneracy that is usually not seen in adiabatic case, but in for isocurvature, the Laplacian bias actually has a nice degeneracy with the signal. Just to give an example plot of what the matter power spectrum would look like. So this is from the FastPM code. You have the blue dots as the adiabatic add some additional power from the isocurvatures. The alpha parameter is just the primordial amplitude. So in this case, the primordial amplitude is 1/4. And as I said, even though the amplitude is 1/4, you get additional suppression from transfer function. So the overall effect is only 1% or so on what we observe today in the matter power spectrum. And yes, because there is a large power on blue scales, the C-square parameter, which is usually the one loop counter term for the EFT of LSS, is not positive, it's rather negative. And that's fine because this is just an EFT parameter, and we did not assume any positivity of these terms. So yes, we do need to do some renormalization. So there are several schemes for this. Finally, to just look at some results, this is what we have. So here we are showing 95% confidence upper limits for CDM blue isocurvature or for the fraction. Planck already places some constraints, and those are about 0.6. So roughly here, if you can see the red dot, I think even I can't see the red dot. Okay, so this is what Planck has, and Euclid's are slightly better. Euclid gives more support. So Planck is largely flat because they do not have enough sensitivity to this slope, and hence their values are almost the same for all the spectral indices. Euclid has a sensitivity, but again, it's not very much. In fact, it's only sensitive of doing slightly better than Euclid on slightly better than Planck for larger n isos. Megamapper, which is kind of a stage 5, what we have been looking at here, does much better than Euclid and Planck. In fact, I will say a factor of 10 improvement for stage 5 surveys. And these are the results in real space. So we also have results for RSD. And if I add RSD, you get a factor of 2 or 3 improvement. The dashed line here the dash curves here actually represent unmarginalized constraints. So marginalization does have a effect that it worsens the overall result, and that is purely because of the nuisance parameters. So in fact, if we have some strong priors on those bias parameters from simulations, we can actually get much better results. For the megamapper, we have two different situations or scenarios. An idealized one, which is the brown, and in fact, some conceptual one, which is this one. And finally, the marginalized one is right here. Just going back to what science case this represents, as I was saying, NISO can offer some insight into the presence of dark matter spectator field. So in future, if we actually detect, or if any of these LSS surveys detect these isocurvatures with a spectral index, then that spectral index directly hints towards the curvature of the radial field. And because, as I was saying, the mass of the axial field is essentially just the curvature of the radial field in this case. So it gives us some indication of it kind of gives us a probe into the inflationary physics and in fact the spectator fields. And NISO greater than 2.4, if ever detected, actually signals time-dependent mass, which means the spectator field was massive during inflation, but at some point of time, its mass had to become 0 and it had to become something like a Goldstern mode. Blue isocurvatures also help relax a lot of HFPQ parameter region. There have been models where you can get some kind of large bumps and even oscillatory signals. So these kind of bumps, which have at least an order 1000 amplitude over the usual flat, can seed your compact objects. And the oscillations here in some models can actually mimic cosmological collider signals. And also, there is a slight indication that if you study the C-square parameter, which is one loop counter term, you can get some indication of isocurvature just by looking at the C-square parameter and seeing the redshift dependence. Finally, I just took a snapshot of Kyle and David's slide while I was sitting back, just to show where isocurvature would rather fit. It would fit somewhere here and here in the whole science goal of this project. Yep, thanks.
Wonderful. Okay, so I think that concludes the list of speakers. Let's hear any questions for this talk first. And then we can have it's all my fault, but we can have like a 5-minute discussion after that. That's more general. So anybody? Okay, well then let's have all the speakers back up and Yeah, yeah, I don't really
Pass this around.
Okay. Well, now let's invite questions for anybody or provocative statements. Some people have advertised things to come out like tonight or something, and if nothing else, I have a selfish interest in this massive particle production analysis, which we could hear more about if no one else has a question, but
You had a question or I can quickly
yeah, could you say a few words?
Yeah. So yeah, it's very much related to the periodic particle production model that you were referring to in your talk, except it's like sort of a more, it's in some sense a weaker version of that, in the sense that we are considering scenarios when there is only a single instant of production instead of something periodic. And it turns out like it's kind of a complementary regime in the sense that you produce very few particles because they're very heavy. So there's not a lot of energy even in the rolling field. So the effects on the power spectrum, the 3-point function, and so on and so forth, those are typically suppressed depending on the parameter space. But individual effects from these particles, like on an individual basis, that can be pretty strong. So in some of the previous work with Yushin and collaborators, we had thought about effects on the CMB, and they typically give rise to sort of localized bright spots or localized cold spots on the CMB. So in this work with Oliver and Colin, we were looking at what does the Planck data tell us about that. So we're basically carrying out the search for that, and it looks like it's pretty powerful. Even if you were to have like one bright spot on the sky, you can constrain it, and it can sort of lets you access particles which are almost 1,000 times heavier than the inflationary Hubble scale.
Yeah, I mean, it sounds like a similar thing in the position space features.
That's right.
Basically, the reason one is able to resum all the endpoint
That's right,
functions in that
exactly.
case. Yeah.
So it also sort of goes along the lines of all the field level analysis stuff that we have been hearing about. Yes.
Okay. Okay. One thing we could do is I listened in yesterday to the sort of senior panel on non-Gaussianity, and they were asked what their favorite observable is, and they had a really small menu to choose from. But I think one of the themes of today is the menu is more elaborate, more interesting than that. So maybe if nothing else, we could ask everybody here what your favorite. Not that we have to choose, really. We should analyze all of these things, but what's your favorite?
Oh, could you please repeat yourself?
What's your favorite thing to look for with these surveys?
I'm like a primordial non-Gaussianity guy, so I'd say FNL local.
So why
but
that one among the plenitude of kinds of?
a simple answer is that that's what I have worked in, so there's a definite bias. Also, from what I see based on all the discussions, is that it's something that's more reachable in some sense than, although, I mean, FNL equilateral as well is, I think, very, I think these are the two parameters that I would say I'm most interested in. From
Okay, so I can turn this around and characterize that answer as being a fan of this highly symmetric case where you have a shift symmetry, so you're choosing from this small menu of low point correlation functions, and that's certainly a case to consider, and that's a interesting answer. Let's go down the line and see what others.
Yeah, I think I'll also have some kind of a bias on isocurvatures, but then beyond that, I'll say cosmological collider signals or primordial features is something that I'm really interested in looking.
So what do you mean by cosmological collider per se? So this is a term that's very catchy. It came up
So
sort of
I
a
think cosmological
few
idea here
years
would
ago.
refer to the interaction terms going into it's looking into the EFT of inflation and looking at all the interaction terms that one can have.
Well, yeah, so that's always the case in any calculation of non-gas entity. Is there something specific about this derivative coupling of the cosmological collider
I
that
think the feature that it imprints on the power spectrum, so one can look for it even just by looking at the power spectrum and try to see what features does it have other than just a scale invariant. And that can be to some extent, for example, the oscillatory features that people have been talking about here. So that can directly be looked at in the power spectrum. Now, regarding bispectrum, I'm not sure, so I'll have to ask other people. I mean, you will have to ask other people if one can also see positive signals or much more in the bispectrum.
Okay, other opinions?
So the question is, what is the favorite observable for this workshop?
Yeah, you're also free to change the subject, right? No, just not this workshop, but just what are
Okay,
you most excited about?
I'm going to say local power non-Gaussianity because it was in the first bullet of Kyle and
Okay.
David's talk yesterday.
okay.
So it's where the data and the community seems to be focusing.
I think first of all, like any detection of non-Gaussian would be fantastic. We don't necessarily have to be exclusive of different scenarios. So if we are looking at equilateral configuration, maybe we'll find something and then we are not able to tell apart different scenarios. But then if you squeeze the shapes, then maybe you get to see more information. Maybe you see oscillations, maybe you see enhancements and things like that. I think the other thing I'm sort of more interested in is also, it was mentioned in the workshop, is are there sort of calculable scenarios in which really like these summary statistics, they're not ideal. So if especially like, if there are like, if we can make a sort of a very solid case where the summary level statistic, I mean, we have had talks on this, but maybe the 2-point or the 3-point or the 4 points, they're not really the ideal candidates, but you want to look at something global. I think that would also be interesting. So just I think thinking about scenarios where we might potentially miss a discovery, I think that's also important, not necessarily tied to FNL local or equilateral or cosmological collider, like oscillatory type signal necessarily. Yeah.
I would say primordial features. So I don't know why primordial non-Gaussian is more popular than primordial features. I asked a few people, and they also don't know why. And I asked Martin, who was here a minute ago. So there seemed to be no particular reason why primordial non-Gaussianity is more popular than primordial features, and primordial features also seem to have well motivated reasons. And also we can just look at power spectrum instead of going to higher order statistics. So that seems to be easier to study, but somehow it's not being looked at very much yet. So and I don't know why. So I think
I have one quick comment on that, which is, I mean, it's also something that was brought up by Austin yesterday. In some sense, if you do have sort of perfect scale invariance, you do not necessarily expect features on the power spectrum. But like in bispectrum or trispectrum, you're accessing ratios of scales. So it's totally fine or totally possible to have like oscillations and other types of effects in the bispectrum or the trispectrum without having any such effect in the power spectrum. So in that sense, it's also related to what Eva was asking. I think there is also some sort of a theoretical prior in the sense that if you do have scale invariance, you do isolate these classes of things. So having a perfect scale invariance does imply that you don't get primordial features. So, but we do not know what happens from the theoretical perspective. But anyway, this is something related to what you said.
Okay, thanks.
I agree with the statement that there's so much interesting stuff to be learned by better and better measurements of the power spectrum before we can go to the bispectrum and so on. So I kind of have the same opinion as Shini, that primordial features are probably most interesting for me.
Okay, well, thanks to all of you. Is there more discussion? And feel free to introduce a new topic. We don't have a lot of time, but Dan, please. Here, I can.
So several of you are working on different aspects of the measurement of local non-Gaussianity. Several brought up serious concerns we might have, and they're not all the same. Should I be triply concerned about how to measure it? Are you, of those of you who are working on local non-Gaussianity, are these problems that we'll solve in time? Are they things we can do to, say, address what's B-phi or, the various other things that introduce scale-dependent bias? Like, what's the sort of most urgent thing you think needs to be done?
I'll just say that the B-phi thing is probably you can say that the triviality of local non-Gaussianity or non-triviality of local non-Gaussianity is more important at this point than it actually having a certain value, because that's going to tell you more than what the value is. So maybe you can consider just constraining the thing B-phi FNL itself, or even if you consider B-phi FNL plus whatever additional stuff that you have, as long as it's non-zero, you're learning something. So that's definitely one thing I'd say at the very least. And the ionizing radiation thing, I think it's too difficult to model to make a statement. But yeah.
I agree with that, and I would also add that even if we can only measure the product of FNL B-phi FNL, it's still interesting, and we can at least know whether FNL is 0, and then we can worry about the B-phi term. So I think before that, we need to be more careful about systematics and to make sure that we don't have a biased estimate of FNL. Yeah, so that's my thinking.
Can I add a follow up to that? Because I think the issue for B-phi, it's also the redshift dependence. Because if it was just a constant times FNL, I agree. It's like, who cares? Just measure the product. But it's the ability to combine different redshift bins, where if you don't know the redshift dependence of B-phi, then you can measure B-phi separately in each bin, but you don't get to combine the constraining power. And is that a fair assessment?
That actually worsens the situation. Like I think you need some handle on what the redshift dependence is going to look like. Like if you just assume these free parameters are different redshifts, you really don't get any useful information. And yeah, I don't know. I don't know if it's an easier problem to pin down the redshift dependence on B-phi than to pin its dependence on the usual galaxy bias. I don't know that.
Do I go?
It's a long 5 minutes. I will just say it never, in your response to your original question, it never hurts to be more concerned. You can be triply concerned, quadruply concerned. Yeah, and we didn't talk about observational systematics, so yeah.
Yeah, you can go ahead and ask.
Okay, I have another question. Oh, I was just past the mic. All right, this might be the last one. Yeah, so this is a question for someone on stage or maybe the whole audience here too. I guess one of my concern or things I'm thinking about is how to model the slightly nonlinear scales for getting local FNL. So I guess some of the I guess we're interested in very squeezed triangles, so covering very large scales, like potentially 10 to the minus 3 h over megaparsec, all the way to hopefully beyond the linear regime, like above 0.1. So I guess some of the results that you guys presented were very focused on above 0.1. So and I get that you can get good measurement of FNL there as well with the squeezed triangle. How much of that would be applicable to once you start to get really large scales like 10 to the minus 3 and all the way to, I don't know, 0.5 or 0.2, 0.3, let's say. So, and I guess my question is like there are various things on the market, like one of the very obvious things is just brute force bispectral nonlinear modeling, which we've seen recent papers on, with EFT parameters and one loop. Like, what would tell me that I should I should choose like say reconstruction, or I should choose the pi field or a response function, like versus that. Like I guess I'm sort of want to hear a little bit from everybody in terms of the pros and cons of this kind of choices. Thanks for that particular use case.
So what kind of issues are you envisioning at larger scales? Do you have anything in particular in mind?
Well, I guess for example, yeah, if we talk about the pi field that you have, it's basically it's binned right there's a W that will be imposed that takes a value 1 for a certain K range, and then but if I want to have a sensitivity to triangles that are highly squeezed, meaning 1 large scales like K of 10 to the minus 3, and then 2 small scales of like 0.3, like would that work, and would that be much better than a typical default like bispectrum EFT one loop modeling, which will be a lot of work and a lot of bias parameters?
Right. So this is something we address in our paper as well. So we are like very good, in a particular regime, which is the squeeze limit, and we are also complementary. So if there are other models which are so while actually performing the real data analysis, there's going to be a complex interplay between several issues. You also want things to be computationally manageable. You also want things to be very robust. So different methodologies are going to give you advantages in different regime. What we have works very well in squeezed and can easily be applied in that regime. If you want to capture information in, say, collateral shapes or some other regimes, it's pretty straightforward. The fact that we are reconstructing a field, a pi field, it becomes very easy to combine other approaches at say map level or even beyond very seamlessly. So one exercise in the future could be to combine all these estimators or strategies together and see if things get better or not, and what works best in what regime can also be addressed in that way.
So to summarize, you're saying it's very easy to extend your methodology, and one should just evaluate.
And the thing that you pointed about binning in W, it turns out that it's the binning which is actually helping us a lot. By optimizing our analysis, because we can compare it with other approaches where people have looked at the constraining power of pi spectrum and they have found information to saturate. But by binning, what we are doing is we are pushing it to a more optimal level, in a sense, and that's helping us gain more information out of nonlinear scales. So yeah.
Okay, thanks.